have a small discussion about on recap of the first day. So if there are any doubts, any questions, you can raise the questions. Is there anything?
Yeah, so we just wanted to check and see if everything was clear. Any questions that people had? I had one or two people come up with very specific questions yesterday at the end of the class, or when we were having the little break at the end. But they were pretty specific questions. So nobody has anything else to bring up from the other day? Okay, we can move forward then, no problem. Let me switch slide decks real quick. So today we talk about conformations. Conformations are really important for medicinal chemistry. So when we think about an enzyme, enzymes are composed of amino acids. Amino acids are mostly chiral molecules. There's one that isn't, right? Glycine is not chiral, but all the other ones are chiral. So when they form a pocket in an enzyme or a receptor, or some other biological target, maybe it's RNA or DNA that we're trying to engage, that's a chiral environment. And so that we nowadays think very much about the chirality of drugs and how drugs will fit in that chiral environment. And fluorine can perturb conformation significantly, and that's what we're going to talk about today. You know, how fluorine can control different conformations. We'll talk about sp3, carbon-carbon bonds bearing fluorine. We'll talk about some other amides bearing fluorine at the alpha position or ortho position of an aromatic ring. We'll talk about how different functional groups engage fluorine differently and help control conformation. Amines, hydroxyl groups, other fluorine atoms. There'll be a variety of different control elements that we'll be talking about. And so again, this is just to help prepare you to think more critically about how to exploit fluorine in medicinal chemistry. So just as a reminder, and I'm going to keep hammering this, the physical organic chemistry is extremely important to understand. And by understanding the physical organic chemistry, you can apply it more intelligently in the design campaigns that you'll be working on in the future. And maybe it's your PhD work, maybe it's your postdoc work, maybe it's in 15 years in industry, or when you're mentoring students. When you're a faculty member mentoring students and you come back and start talking about conformations and how to improve the quality of interactions with between your drug and your target. So specifically today, this is the roadmap. We're going to be talking about linear and cyclic systems, so we're going to be talking quite a bit about a few different types of interactions. We will be discussing the hydrogen bonding interactions, and I'll say several times in this course, inter and intramolecular hydrogen bonds are very different with fluorinated substructures. And so in this lecture today, we're going to be talking about the intramolecular hydrogen bonding interactions. We'll be talking quite a bit about dipoles. And in order to understand the dipoles, we'll talk quite a bit about magnets. And just think of like back when you were a kid and you're playing with magnets in the house, in the kitchen, the bathroom, wherever you're playing with magnets. Think about how those interacted, and we're going to come back to that analogy when we talk about different orientations there. And then we'll be talking about quite a bit about Newman projections and how fluorine can help control the different substituents around a CSP3 bond. Okay, so that's the kind of roadmap for what we'll be talking about. And we're going to start right away with that final topic that I just mentioned here, looking at CSP3 bonds. So fluorine can control conformations, and specifically, we need to draw analogy to, first, I want to reintroduce an area that you all are likely more familiar with, and that's like if you had an oxygen there. And then we'll compare it to what happens with fluorine in the second step. Okay. So when we look at maybe a compound that has a hydroxyl group in it here, we typically rationalize the more favorable conformations through an anomeric effect. Anomeric effects would be something like a lone pair of electrons on the atom that's on the back side. Remember, this is a carbon atom on the front, and then in the back you have another carbon atom, and so that group is attached to the carbon atom in the back. And this would be the lone pair of electrons. Those lone pair of electrons donate into the sigma star orbital of the CO bond, and that's a stabilizing interaction. Okay, so it's a really basic phys-org principle. That anomeric effect encourages the molecule to exist in the conformation in which that lone pair is anti to the hydroxyl group. And for oxygen-containing compounds, you'll typically see this anomeric effect override gauche interactions. Now for fluorine, the opposite is true. Fluorine prefers to exist in a gauche conformation. So gauche meaning these are 60 degrees apart, the X and the fluorine group. And so the equilibrium here will lie in the opposite direction. And it's an important conformational control element for the simple model system. We just have hydrogen, 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 hydrogen around the ring. But in other situations, you might have other carbon substituents or other things that are built around the drug or your materials, right? So the gauche effect dominates over the anomeric effect when you have fluorinated compounds. And in order to rationalize that, we use several different models, energy orbital overlap diagrams, and also this type of a visualization. So specifically, we can start with this one over here. Again, we're looking at the gauche conformation relative to the anti-conformation. The gauche conformation is predominantly stabilized by vicinal CH bonds donating into the sigma star. So this is the sigma bond. Remember, there's a big sigma star over here on the back side of that orbital, and it's a donation of the sigma CH into the sigma star of the CF. And that's a stabilizing interaction. That interaction is shown over on the other side of the slide. You have 2 electrons in that CH bond. Those are there. There are no electrons in the sigma star of the CF bond. That would be the one that would be presented right here on the back side of that would be in this space. Okay. And the donation of those electrons into the sigma star creates a hybrid molecular orbital, and 2 electrons will go down into the hybrid orbital. When we make a hybrid orbital, because of orbital conservation of orbitals, we make a bonding orbital and an anti-bonding orbital. And so we have 2 electrons that go down into the bonding orbital, and no electrons go up into the anti-bonding orbital. And as a result, we have a net stabilization of this conformation over here because of this type of an electronic configuration. Okay. So this is basic phys-org bonding theory. And that's the reason why this conformation is more stable. You have to have a CH bond presenting into the sigma star. When that CH bond presents into the sigma star, that will mean that the X group and the H, in this case for this model, are at 60 degrees relative to the fluorine atom there. Okay, so it's an important conformational control element. Now, how strong is that interaction? That's going to be important. How much of a rotational barrier is there to overcome this interaction? And that's what's shown on the bottom of the slide. That X group can be many different things. There's no shortage of things that you could imagine there. And so we're just going to scan a subset of these groups. You can see if you have a fluorine atom there, so that would be like a vicinal 1,2 difluoro-containing compound. That energy is reasonably low, half kcal to 1 kcal per mole, usually. Okay, that definitely gives a preference for one conformation relative to the other, but it's reasonably weak overall in energy. Similarly, if you just have a hydroxyl group, that's a reasonably weak interaction. As you get to acetates and the inverse ester, right? This is an ester that's also an ester, but they're connected differently. One's connected through oxygen, the other one's connected through the carbon. So those about a little over kcal, kcal and a half. And then you see this massive difference in conformational control energies when you look at neutral versus cationic species. That's a really important difference there. When you get charged amines, any charged species, you see this massive preference for the gauche interaction. Really important. We're going to look at that in more detail in 10 slides or so. It'll be a little bit further down, but we're going to come back to that. That's a really powerful control element. Okay. Amides, pyridines, you can have other things there too that help control the conformation. And these are just estimates for a model system. Any specific system where you have other groups dangling off your molecule, there might be perturbations to the overall energies there. Okay? So that's a really basic principle here. That's the first basic principle. The second one comes back to dipoles and magnetism. So this is going to be a slightly different model system. This is a model system in which we have a series of carbonyl-containing compounds and a fluorine atom at the alpha position. In this model system, we have a variety of different groups here at this position. You can see amides, esters, ketones, aldehyde. This type of a system prefers an orientation in which the fluorine atom is actually aligned anti to the carbonyl oxygen. And this is the situation that I had mentioned before where we're going to think about magnets. And if you are a kid and you're playing with magnets, you've done this before. Okay, you have your magnets. They have a positive and a negative side. We know about what sides engage each other and which sides repulse each other. You ever try to hold them together, fully aligned? They don't like that. You ever try to hold the bottoms together and see what happens with the tops? The tops push away. And they'll push away as much as possible. And that's the same effect that you're seeing here. You have the carbon-fluorine bond as a dipole. You have the carbon-oxygen bond as a dipole. Carbon-oxygen double bond, right, and has a dipole. The dipoles present, they're cationic on the carbon, they're anionic over on the fluorine or the oxygen. And so when we look at this model, we can see that you can't change the distance between the positive side. Regardless of what conformation, those are held at a fixed difference. But the anionic portions, the anionic repulsion, can push the oxygen far away from the fluorine as much as possible, and that's what we're seeing here. So it's an electrostatic repulsion effect that gives you these energies. Those energies inversely correlate with the electron density on the oxygen. We learned this when we think about early organic chemistry and electronic structure, is you have a carbonyl and you have substituents with lone pair of electrons that can donate into the carbonyl. That increases the anionic character at oxygen. And so that increases the strength of the dipole. When you increase the strength of the dipole, you're going to have greater electrostatic repulsion here. And as you go through the series, oxygen can still donate in, not as well as nitrogen, but you see a little less electron density on oxygen, a little lower repulsion energy there, conformational control energy. Ketones, no lone pair of electrons. They cannot donate in through some type of a hyperconjugation of lone pair of electrons. Nonetheless, the carbon is still somewhat donating into the system through a sigma effect, and that's what you see here, and the aldehydes are way over there. Okay. So that's one important effect. This electrostatic repulsion really pushing the electronegative atoms away from each other. Now, in another model system, we can also see that hydrogen bonding, intramolecular hydrogen bonding, can further reinforce conformations. So in addition to the dipole repulsion, this model system that we're looking at here, that has an amide, alpha carbon with a fluorine atom, and then some other group attached, this model system can have several conformations. The most stable conformation is the one in which the dipoles of the CO and the CF bonds have, again, rotated away from each other. But this system also benefits from an intramolecular hydrogen bond. The intramolecular hydrogen bonding does happen, it is real, it is a real effect in fluorine chemistry. It's not particularly controversial. Now, as we rotate around the CC bond here, you can rotate it such that we lose the the intramolecular hydrogen bond, and those dipoles between the CF bond and the CO bond come closer together, 6 kcal per mole. That's a lot. And here's another example where we further rotate the molecule. So this is from here to there, that's 180 degrees. And again, those dipoles start to align. And that's disfavored, 8 kcal per mole. That is very, very, very unhappy. Okay, if you want to do a quick calculation in your free time, you can take 8 kcal per mole. RTLNK, what's the equilibrium? What's the ratio for 8 kcal per mole? This thing does not exist. Okay, go do that math at some point. 8 kcal per mole, what's the equilibrium distribution of those species? And rationalize to yourself how powerful of an effect that is. Okay. So in this case, we have two things reinforcing. Now think of how you might exploit this in a drug discovery campaign. This model system has methyl and methyl. Methyl on the amide, methyl alpha to the amide. If you have bigger substituents built onto that engage your biological target, heterocycles, arrow rings, other pharmacophores you might have, you can really encourage a conformation in which we have control of the stereocenter, which might benefit engagement with any particular target. Okay? So we saw yesterday in the synthetic lecture some of those alpha fluoroaldehydes and other carbonyl-containing compounds, and you can really build around them very well when you can make them enantio selectively, and that can be a really powerful conformational control element if you use it. Okay? So I'll pause. We went through a couple of effects. We went through the gauche interactions. We went through these that are an electrostatic repulsion and then combined it with an intramolecular hydrogen bonding interaction. I'm going to pause and see if there's any questions or.
In the first case, even there is in the case of OH, okay, so there also there is a dipole because CO. So will that why that doesn't predominate?
Sorry, in this one here.
Yeah, like for example, if you take these two Gauss effects predominate those pictures, so because that OH dipole and our CF dipole. So
Yeah, so
form also.
maybe one thing when we talk about a lot of these oxygen-containing compounds, when we're thinking about what is the X group, most commonly it's lone pair of electrons that we're talking about, like sugar, saccharide chemistry, and things. So the nature of the X group in these cases is usually lone pair of electrons. Just are great at hyperconjugating into the sigma star. Yeah, it's a key difference here. In contrast, if you have fluorine and you have lone pair of electrons that are nucleophilic, what happens, say we have some type of a functional group that allows us to make a full-blown anion. These are not particularly stable. If you have lone pair of electrons alpha, they'll typically push off your fluorine. And then you get to some type of alkene type species. If it's instead like a nitrogen without a proper protecting group, same thing, lone pair of electrons will give you an imine. If you have a hydroxyl group, if it's OH, lone pair of electrons will push off your fluoride and make an aldehyde or ketone depending on what else is attached. Similarly, if you have like O and E or something like that, less of an effect. So there are lots of nuances as you continue to build and build and build on it. Yep.
So I didn't quite understand that the middle family. So the sigma CH bond, the sigma electrons can actually participate in the gauche form.
Yeah, this one.
Yeah, this one. So you can actually have that little stabilization which is coming up. But then this one, the bottom one, when you have this anomeric form, so why that CX cannot really donate into that because it's a mismatch in the energy of the orbital, or how is it? Why is this?
Yeah, I think it's an orbital mismatch, and so when you have the CX it's like an oxygen or fluorine or something, that bond gets stabilized quite a bit more.
Okay. And anyway, the
And
sigma
so it
star
doesn't-
of that one is very high,
and that would be
this
a-
one's down. So is it this, because of the orbital mismatch, it doesn't happen. That is this figure.
Right, right. You want to be thinking about orbital mismatches for sure. Yep. Yep. And these are all, you can use quantum mechanic, Gaussian, and things like that to estimate specific examples too. And you can see these types of interactions when you do a Gaussian calculation and you look at the different orbital energies. You can see these interactions pretty clearly.
But then, so this you are deconvoluting this effect completely with the electrostatic repulsion effect. But in a way, this combines with that to give that, right?
Yeah, depending on what type of a model system you have versus your real system, you can have several effects reinforcing each other, or they can be working against each other. You can also design systems that work against each other, and then you kind of get like no effect, right? Or minimize each other, right? So I think any of these effects, you want to be really critical at how you think about use them think critically when you're trying to use them in your molecules, right? Because they can be working against each other or they can reinforce each other. Yep. Okay. So this is maybe the first example, and this is going to be an initial example that we're going to cover briefly, but the tutorial today is there's a lot of stuff in there. We're going to come back to this exact molecule in the tutorial. So my discussion right now is going to be maybe a little bit more brief than it should get, but it's because we're going to come back to it. So this is an approved therapeutic, not used very much anymore. It's an older therapeutic. I think it was approved in the early 90s in Dinavir. It's an HIV protease inhibitor. You can recognize a lot of these HIV protease inhibitors by the secondary alcohol right in the middle of the molecule. And as a protease inhibitor, the role of a protease is to cut up peptides, right? And so those peptides have a bunch of amino acids. And the proteases recognize very specific amino acid sequences. So they have certain pockets. We call them S1, S2, S3 pocket. If you go one way, S1 prime, 2 prime, 3 prime, and those are pockets in the enzyme that fit very specific amino acid sequences. And when these HIV drugs, when you look at them, you see that secondary alcohol, but you also see certain moieties that fit into the pockets that a peptide side chain would normally fit into. So these are either peptide-based or peptidomimetic drugs typically for these HIV protease inhibitors. And this is one of the first generation ones. This thing gets metabolized so quickly. Patients have to take 4 rounds of drug a day for like every day of their life with these older generation agents. And the newer agents have solved a lot of the PK problems. Anyway, this story is really going to be about conformational control over a linear system. You don't see as many drugs that have these really long linear systems because they're typically so flexible, they're very wobbly. And in this case, in these HIV protease inhibitors, many of them do have extended aliphatic chains. So this drug itself has a Ki value of 1.9 nanomolar, so pretty potent of a compound there. Interestingly, when you switch the alcohol, you change the conformation. And when you do that, look at the inhibitory potency there. Pretty drastic change, right? 80-fold change just by one stereo center. So what difference does a stereo center make? It can be pretty powerful when you get it right. In this example, this is an older example from '86, the introduction of a fluorine atom alpha to that alcohol in this species here, the active drug, gives you no benefit, 2 nanomolar still. And within the errors of the measurement, that's probably the exact same number statistically. So no benefit. Why? I'm going to talk about that in just a second. Let's look at the other one. In contrast, when you have the secondary alcohol over here, you can put a fluorine atom with appropriate stereochemistry and rescue quite a bit of the activity. 8-fold improvement by a fluorine atom. So what's going on in the system? Let's think about what section we're on. We're talking about conformation control and fluorine. I've introduced this gauche interaction. What's going on in this system, the molecule needs a certain conformation to fit in the protease pocket. when we introduce a fluorine atom here, we get no gain in potency, and that's because the introduction of the fluorine atom will favor a gauche interaction. But if that's already the natural conformation of this drug, if it already sits in that same conformation, you really don't get much benefit. It had the right conformation before, it still has the right conformation, everything's good. In contrast, when we go to this derivative over here, you have the wrong conformation. That alcohol's in the wrong position, wrong stereochemistry there. And so in order to get this type of potency, it's even got to like rotate around unnatural poses to engage in the target. But we can encourage this molecule with the wrong stereochemistry to exist in the right conformation as much as possible using a fluorine atom. So we can just force that to go back to its normal conformation. Now that's vague. It's a little bit nebulous right now. Who knows Newman projections, right? Everybody knows Newman projection? Please, everybody, right? Even our master's students who are early in their course, you know your Newmans, right? Okay, good. And we're going to do that in a complex setting in the tutorial. So you're going to explain this in more detail in a little bit, so get ready for that. Okay, so are we good with this more complex example for a bit? We'll come back to it. Any questions you want to address now? Okay, let's keep going. So conformation can also control ring systems. So this is a ring system, a pyrrolidine ring system. In this model system, you have a carbonyl at one position, you have an amide over here. We have 6-membered rings. We're talking about bow conformations and chair conformations and chair flips, and 5-membered rings are typically a little bit more simple. You really have 2 puck rings. You have one puck ring in which the 5-membered ring, so if these 3 are kind of close to coplanar, then you can pucker the ring one way, or that carbon can flip the other way, and that's what you see here. So you have 2 different envelope conformations there. And they can interconvert, and fluorine can control which one of those predominates. Now, when these, so the naming that I'm going to use, the exo and the endo, the exo really refers to the pucker being away from the carbonyl, and in this case, the pucker is close to the carbonyl there. So it's the endo-exo there. Fluorine can control the energy levels of these 2 conformations. So if you need, for example, a conformation that's exo, we can decorate this ring of fluorine and encourage that conformation, and we can do the same to promote the endo conformation also. Okay, so how are we going to do that, and why does it work? So here's that model system, and we can fluorinate the C4 position here. So I'm going to start here, 1, 2, 3, 4. This is a C4 position. In this case, we're going to look at compounds having either a hydrogen, a fluorine at these 2 positions. So if you have the non-fluorinated species, you have a 1 kcal per mole preference for the endo conformation, and that's this one over here. There's a slight preference for that to exist endo. When you introduce a fluorine atom here at the X group, and I've drawn it in there for you, you can invert the selectivity. You can prefer the exo conformation. That's a 2 kcal per mole change, right? It's about 1, and it goes to -1. 2 kcal per mole change. Okay, it's a useful effect to control the conformation. If we want to reinforce the other conformation, we want to reinforce the endo conformation, we can introduce the fluorine atom with the opposite stereochemistry. And that's going to encourage that to exist in the endo. Finally, if we put 2 fluorine atoms in there, they work against each other. Neither one of them wins out. You go back to 1 kcal per mole, which is equi-energetic basically for all practical purposes with where we were to start. Now, you might want to have 2 fluorine atoms for a different reason. There are many reasons you can use fluorine. We'll talk about more reasons in future slide decks. But you get no benefit for conformational control with the CF2 because they're working against each other. Now, I think it would be a great exercise. We're not going to do this here now. We're going to look at some other systems in the tutorial. But I think it would be great for you on your own time to come back and look at these systems and think about the Newman projection there, and make sure you can see in your mind the anti-alignment between the CF and the CN bonds there. Make sure you can see how that maps onto that first slide we talked about. And same thing over here, it's a little bit trickier. So that was kind of, you can see that one, I think, a little bit more easily the way I've drawn it. This one's a little bit tougher to see, that there's a gauche interaction there. Okay, so that the CN is kind of down and to the right, the CF is kind of up to the right. If you build a 3D model of that, or some people in their head are just really good at seeing these things in 3D and thinking about, if I put myself, over here where this oxygen is, if I look that way, mentally, I can see what's around, and they're gauche. So I think it'd be a great exercise, ball and stick, back in your offices, in your labs. But we're going to, again, look at other model systems of this type of effect during the tutorial later, too. Okay? Questions? Comments? We doing good? Okay. So, we already covered, yep.
In counselor, in the third case, why the N2 is fluorine, don't you think that the fluorine electrons and oxygen electrons of carbonyl will get repulsed to each other?
Yeah, I mean, that's reasonable to say, the way it's drawn here. But you also have free rotation around this carbon-carbon bond, so the carbonyl can rotate and adopt a conformation which the carbonyl oxygen is not towards the fluorine. So that can happen. And I can't really draw all the different possibilities quite as well. So, okay. So you have counteracting effects there in this last one. And I want to step forward into this example. I've already introduced this gauche effect and said it's a weak effect when you have fluorine-fluorine, but it's there, it's present, it can be useful. There's another effect when you effectively use fluorine patterning, and that's this 1,3 effect. The 1,3 effect is actually pretty powerful, 3 kcal per mole in energy. You can see the representative model system we're looking at here in this 1,3 system. It can exist in a conformation in which those dipoles are aligned. That's bad, that's terrible, right? But if you rotate around one of the CC bonds, it can reorganize such that the 2 CF bonds are presented away from each other. And in that case, that's a 3 kcal per mole energy difference, and this conformation is favored. And that can be exploited intelligently, and there's some really cool model systems that I've seen out there. We'll look at a couple like super nerdy cool ones. So this is one in which we use fluorine patterning to mimic control of a ring, but we're going to remove the ring. This is really cool, okay? So in this model system, we have a dihydrobenzofuran, a methylene, and then some other moiety over here, an arrow ring in this case. The NMR structure and computational structure gives you something that looks like this. In this case, with fluorine patterning, we can recapitulate the solution structure of the molecule on the top using fluorine. So this molecule on top is pretty rigid, right? You cannot do much rotation around the bonds over here. They're pretty much locked. You get a little bit of flexibility in the ring because it's partially aliphatic. But remember, this is sp2, so you don't get as much flexibility in this molecule as you would with like a fully aliphatic system. Okay. So you don't get too much flexibility in this system. In this case, you might envision rotating around all the carbon-carbon bonds here. You have several CSP3 bonds there in a row. Nonetheless, using fluorine patterning, we can create a molecule such that the aromatic rings reside in the same chemical space. The aromatic ring over here and here reside in the same chemical space. And these are, NMR structures and computational structures that both reinforce. So you have computational estimates and real data. And again, the nature of those reactions is this 1,3 dipole, and you can see that here. And this is the computational structure here. The 1 fluorine atom there, the 2, the 3 is over here, and they're rotated such that they're presenting away from each other. So a pretty cool system over like that.
So in this case, the dipole, if you have 1,3 interactions, the dipole orients in such a way that the dipolar reinforcement does not happen. It actually kind of cancels it out, because otherwise there will be a strong electrostatic repulsion as well, right?
Yeah, so the electrostatic repulsion is what we're trying to avoid.
Yeah.
Yep.
So dipole of the molecule goes down. Overall dipole, resultant dipole.
Yeah, so you would have a stronger dipole if they were aligned,
Exactly.
and that gives you a less of a dipole. You do still have a dipole because the dipole will be the sum of the two dipoles.
Right.
Another heteroatoms and anything else,
Not
but
that in
yeah, they won't be fully additive. Yep, right. We'll talk about dipoles a bit more when we get into the lipophilicity lecture. We'll have a series of molecules that I think might interest you to think about. Okay. So that's a really cool system. Conformational control with fluorine, 1,2 and 1,3 has been used in several other settings. Here's just a couple of nice papers that one could look at that look at some simple systems. I'm going to look at this crazy looking system right there next. Just going to give you a second to look at that molecule. Right, we have a 1,2, a 1,2, right? Because fluorine 1,2, that's real with an oxygen-based group. We have a 1,3 there. We have a 1,3 there. Like there's a lot of stuff going on. And think about the synthesis of that thing. How are you going to prepare that with all the stereo control? So if you want a hint on how to do that, Eric Carrera, this paper right here teaches you how to do it. It's really cool. Something else really cool about it, and I'll come back to that in a minute. So this molecule has a very distinct conformational preference, and it can be worked out with exhaustive NMR, really thoughtful NMR. It's well laid out in the supporting information of this manuscript. I'm not sure if it'll be covered later in the NMR lecture or not. And so let's look at what's going on in the structure when they do these NMR studies and look at the coupling constants that tell you roughly the geometry, the relationship of the fluorine atoms and the other heteroatoms. So we're going to start here. This fluorine atom needs to be gauche with this one, and they are. See that? That's gauche there? Okay. Now we have 1,3 interactions. If we go from here, 2, 3, that's a 1,3 interaction. And they don't want to align both parallel. They're going to rotate so that they're, again, presented away from each other. So that's a really cool 1,3 interaction here. We're also going to have a 1,3 interaction here between this fluorine atom and this one over there. So we're going to have a pretty rigid control element all the way over here, right? And that's looking over here in the molecule. Now there's a C7. We're not worried about what's going on way over on the far side, right? We're just worried about this section over here. You have gauche interactions here between the fluorine and the sulfate there. Okay, so it's a really cool, really rigid system in which they've used fluorine strategically just to pattern this entire thing. And this is a natural product derivative, and maybe it can be useful for drug discovery, but this is like the extent of, just a really cool system, I think. Okay? I drew up a couple of other bad ones in your slides of like things that wouldn't be good. Okay, so you can think of all these other isomers and draw up crazy ones, and so in this case, if we had the wrong stereochemistry on one of these, we would have like a poor 1,3 dipole there, because that sulfate is anionic too. So it's going to want to push away from the fluorine atom. Again, we're staying away from systems in which we have the syn alignment of the two dipoles, another one over here. So I just drew all these other things that wouldn't be good if they form, just so you can think about it. Okay? So I'm going to pause again, see how things are going. I think in your slides I gave you all these. I just didn't color code them, right? So that's for you guys. I deliberately do that for you guys to be taking notes and drawing things and being active with your slides. Okay, your notes are just kind of black and white there. Okay. Good? Okay. So let's think about what else is going on in these systems. I mentioned that there's intramolecular hydrogen bonding, and it's real. Now I want to show a couple of situations that further reinforce this concept of intramolecular hydrogen bonding and show that it's different than the dipoles, but they can reinforce each other. So that's the goal here. This is a piperidine example, a classic example again, that has a nitrogen and a fluorine atom at vicinal positions. We have the gauche relationship here when the fluorine is in the axial position. And when you do the ring flip and put that in the equatorial position, you get a lower energy conformation. That ring flip is not favorable. And usually when we think about these ring flips, we say most elements, most substituents want to be in the equatorial conformation and not the axial conformation. Fluorine's the exact opposite when it's here next to a cationic amine. So it's an important, powerful conformational controlling element when you get to the 5 kcal per mole, 5.5 kcal per mole energy there. Very useful. Now think about if you had a 5 kcal per mole preference for one conformer, you perhaps could force other substituents into axial positions that might not otherwise want to exist in axial conformation. So say we had, for example, a methyl group axial at this position. That's a pretty low A value. The fluorine would dominate in the system. So you could present things at vectors that might be difficult to do otherwise due to your classical A values. Okay? So you can use that strategically at your choosing. So this is a nice paper that establishes a difference between intramolecular hydrogen bonding interactions and the dipole, the Gauche effect. Okay, so we're going to look at a series of examples here on this slide in which computationally we're looking at a Gauche versus anti-conformation if we stop intramolecular hydrogen bonding. So we're not going to allow intramolecular hydrogen bonding in this interaction. This anti-conformation seems to take preference. That might be a dipole minimization type argument. In contrast, when we force a hydrogen bonding interaction, the Gauche conformation, we get about 2 kcal per mole energy there. So we estimate the intramolecular hydrogen bonding to be about 2 kcal per mole, and same thing on the next one. So in this case, we have an oxygen-containing group, nearly equi-energetic, and from computational purposes, 0.3 kcal per mole is like within the error for many computations. And so we'll say these are equi-energetic. When we disallow intramolecular hydrogen bonding, but we get a 2 kcal per mole preference for the Gauche interaction when we also have the intramolecular hydrogen bonding occurring also. Okay, so we can control conformation. Again, in this model system, you only have HHHH, but in a drug, or medicinal agent, or biological probe, you can have other things dangling off the molecule and making interactions with your target. Okay, so the energy estimates for those, I mentioned before, 1.7, 1.9, that range of 1.5 to 2 kcal per mole is what you want to be thinking about when you're thinking about intramolecular hydrogen bonding interactions with a fluorine atom and an acidic hydroxyl or amine. Now, you get stronger interactions when you have cationic amines. And these become even more powerful. You can see the energies associated with these species. Again, this is a model system in which you have a cationic oxygen atom with a more acidic proton making intramolecular hydrogen bond there. You can see the energy difference is closer to 3 kcal per mole when we look at these two structures. These two calculations, one that allows intramolecular hydrogen bonding, the other one that does not intramolecular hydrogen bond. So that's one estimate. Here's another couple of estimates here. When you have cationic amines, again, really powerful conformational control here, and the Gauche is always, always, always preferred. Okay? So I'm going to pause again, see if there's any questions on this series here, yeah, or the previous one, but yeah.
No, not this one only. Like in my last talk, like I was showing some data regarding the hydrogen bonds involving fluorine, and it was quite interesting that CHF hydrogen bonds predominate like more. So in this particular case, the first row, so those two like methylene, the hydrogens, like which is alpha to nitrogen, if one of the hydrogen is replaced to methyl, CH3, will it predominate in the conformational change so that it will become a CH?
Yeah. I don't think it would. Like, I think if you replace one of these methyl groups, if you replace one of these hydrogens with a methyl group, would you have a CH bond here with the CF? I don't think so. And inter versus intramolecular hydrogen bonds are very different. And so, so I think the data you were talking about was intermolecular, right? And so yep. And so the intramolecular, we see lots of examples in the literature and crystallographic database, and it's usually acidic NH-OH that engage in these intramolecular hydrogen bonds. That's pretty well established, and it's been studied computationally and solution structures, and this is well documented. But in the intermolecular hydrogen bonds, number one, I think it's actually a different effect. It's a dipole effect more than a hydrogen bonding effect, which is much weaker. And we'll cover it on Thursday, Friday. I think Friday. That'll be a subset. Okay, we will definitely go into detail on that. Okay, inter and intramolecular hydrogen bonds are totally different. And again, I don't think there's a lot of argument in the literature about intermolecular hydrogen bonds, even recently. And some people say just don't even think about it as a hydrogen bond, just think about it as positive, like a dipole-dipole interaction that's favorable. Oops.
Excuse me, sir. In one of the last examples, is there a possibility of interactions with the pi surface of the pi electron cloud? So that is where the structure is stabilized.
Yeah, so the pi interaction, yes, I think there's an interaction there. Let me point out one thing, though. In this paper, they also do a calculation, and it's a really weird calculation, because when you look at the electronic structure of that, you can see why it's cationic, right? Nitrogen with 4 bonds. They actually do a calculation where they throw an electron into it so that it's a neutral pyridine. Weird to think about what the structure of that thing is. And you lose a lot of the affinity. So in this one, the charge is really important for the alignment there. And I think you do have a pseudo cationic pyridinium in the pi system that does want more electrons, and the fluorine does have more electrons around it. And so there's an electrostatic effect there. The electrostatic effect is real.
Otherwise, there will be electrostatic repulsions between the pi electron cloud and the
Yeah. So if you had a ring here that was instead of a nitrogen, it was like a paramethoxyphenyl or a paradimethylaminophenyl, you probably see that rotate away and hate being in that environment. Yep.
So the pi electron surface should be reduced in electron density, then only it will have an
Yeah. Yeah. And in some cases with really electron deficient heterocycles, you could invert the quadrupole, right, and get to those like a pi acid instead of a pi base. Okay. So here's the summary. Intramolecular hydrogen bonding, good. 2 kcal per mole, kcal per mole and a half, maybe up to 2.5 in some cases. I think we just had this discussion about intermolecular hydrogen bonding. Not always great, but we talk about this in depth. So you have this slide, it's there, but I'm not going to talk much here because we're going to talk about it later. But I've mentioned this several times, there's a difference between the inter and the intramolecular engagements there. Okay, so let's look at a couple more examples here. I do want to spend a little bit of time on this one. So this is an example in which fluorine was used to control the conformation. And in this system, there was a lead molecule that had this imide structure to it. You can see the efficacy in a cellular assay, and then the inhibitory potency in an enzymatic assay. Okay, STING immunomodulators. This is a hot area, hot target here, the STING pathway. But that's the parent structure here. Now, if you remove that carbonyl right there and go to an amide, we lose a ring system that's really holding this substituent, kind of encouraging it to present in one direction. So when we break this ring system here, now we have conformational rotation, we have flexibility around this ring system, and that thing can be it's a bit more wobbly. And you lose cellular efficacy and inhibitory potency. Okay, you lose both of those. The NMR chemical shift, this will be important just a little bit. You can see that NH bond is there in DMSO, and that's this NH right there. You can regain potency by introducing an orthofluorine atom. And you can see the position here. We make a nice little ring system, intramolecular hydrogen bond is worth a couple of kcal per mole, and we regain a substantial amount in potency, not the entire amount, but it's still pretty good for an acyclic system that's supposed to be mimicking a cyclic system, so that's kind of cool. And you can do that the same thing with a chlorine atom there. Yeah, we can talk about that in a minute. I do want to point out, I'm going to mention this twice in the series of lectures, how do you measure an intramolecular hydrogen bond and establish that it's really there? We can speculate about them. There's a really easy NMR experiment to do. It's called ANMR. You measure the NMR in two different solvents. You measure the NMR in chloroform and DMSO. Chloroform does not engage in hydrogen bonds. DMSO, it's a base. So in chloroform, you would expect this intramolecular hydrogen bond to be really tight in DMSO, where DMSO, that oxygen, anionic oxygen, is competing for hydrogen bonding with that hydrogen. You should see a shift. And then you can look at there's a mathematical function that compares the chemical shift in DMSO versus the chloroform, and you can establish quantitatively that there is a good strong intramolecular hydrogen bond or not. Okay, so that's this Abraham paper, ANMR. If you ever want to look that up, it's in your slide deck there. And we do come back to it, and I do actually have the equation thrown on a subsequent slide in a later slide deck, so I'll mention that a second time. But it's a really nice way to experimentally establish that you have a real interaction there. It's not dependent on fluorine. Like this ANMR does not require you to have a fluorine atom. It can be other intramolecular hydrogen bond type situations too. So it's a nice assay that can be run pretty quickly. 2 NMRs. Okay.
So I'm quite surprised to see that chlorine is doing better job than fluorine here, because I would expect that fluorine would actually have strong intramolecular hydrogen bonding, which
Sure.
in the case it's bringing down to 30.3. But in the other case, the fluorine is doing better than fluorine. I mean, that's something surprising.
Yeah. So.
I expect that.
And I agree, but there's something else going on too. So when you just look at the size of chlorine and the electronic cloud around chlorine, it's bigger and bigger and bigger. And I think you're going to have repulsion between the oxygen if it tries to rotate towards the chlorine. So if you think about rotating around this CC bond here such that the oxygen would present over here, now it's going to be closer to that chlorine atom that's huge. This is all rationalization in my mind, not necessarily there's experimental data for it or computational. I mean, you could probably do a quick computational scan of the energies and see if it's a steric effect, basically, or electronic repulsion between chlorine is still delta negative, and the oxygen has a lot of delta minus charge too.
I think it makes sense because it is still providing the computational rigidity required, because overall in 52, that is LSA 52, it needed a rigidity, and the chlorine, the bigger size, it is avoiding the conformational switch that carbon goes up, and maybe that introduces.
Yeah, I do not remember off the top of my head, and we should probably go back in like the tea break and do a quick search, pull this paper up. I don't have my Purdue credentials. We can maybe somebody else can do this, like at the tea break. Check that Zhao, JMed Chem, who's going to be our motivated student. Do they do ANMR for compound C? Because that might establish if there's a real hydrogen bond or not for the chloride. And again, I don't remember off the top of my head, but maybe that would start to get to it. Okay, here's another example too. So the tutorial is going to take, it's going to be a long tutorial. Okay, so I'm going to skim through this slide reasonably quickly. This is the last example, and then we'll break, but the tutorial is going to be a good one. Okay, so let's quickly look at this one. This is another example for which you can see the biological probe here. We're looking at another acyl pyrrolidine system here. We're looking at the forward position of that pyrrolidine and thinking about fluorination of that position. In this case, there's a series of compounds here. The parent compound inhibits thrombin. These other targets here are other enzymes with similar activity they're trying to avoid. So those are anti-targets where we're trying to avoid those interactions. In this case, you can put a fluorine atom here, the X position, that improves potency a little bit. Actually, you get an improvement in selectivity, and for many times in drug discovery, disfavoring an anti-target can be as powerful or sometimes more important than improving activity at your real target. You can avoid tox, you can avoid other types of things going on in cells by avoiding anti-targets. And I think that's something to think about when you look at this series of data. Many of us would look at 0.6 versus 0.4 and say, that's not that big of a change. Okay, but if we can improve potency maybe a little bit, but also decrease potency against an anti-target, that there's value there. Okay, so if you put the fluorine in there with the wrong stereochemistry, you ablate activity. So if you're ever trying this for real, maybe a lesson is, you might need to try both of them. You might not need to try only one, and if it goes terrible and everything's god-awful, maybe you just need to make the other one also and try it at the same time. And you can put them both in, and you lose activity in both those cases, okay? So there, in some cases, might be a little bit more to talk about some of these other interactions here. It'll make more sense when we cover 5, like lecture 5. But if you have lone pair of electrons from fluorine presented towards a pi-rich system, that's disfavored. Right? A pi-rich system has a lot of electron density in it. And if you put that fluorine as the dipole, the anionic side of that dipole is presented towards an electron-rich aromatic ring, you get electronic repulsion, and that's bad. So that's another reason why this is actually a bad compound, is when you put the fluorine in that position, you lose potency that way, okay? So in this case, I'm going to end here with this example. We can take our break. When we come back, you all are going to be using your pens, your papers, your iPads, your styluses, and we'll do some problem solving, okay? See some cool examples, all right? So how long should our break be? It's 11:03 now. 11:15. Okay. So we'll pause now. You all can breathe. We'll come back in a bit. Are we back on the camera? Are we live? So we'll go ahead and start some of the tutorial. All right. So we'll. Connection of the C alpha C beta bond. Okay, you might use that disconnection in practice. You might not use it, but as a synthetic chemist, you always think about that disconnection. Okay. So we would need a difluorinated enolate. We would need some type of an electrophile. It can be an SN1 reaction, SN2 reaction. Who knows? You'd have to eventually attach some type of leaving group to that position. That's the disconnection we think about. And so in order to make this type of a difluoroenolate, one might try to do a deprotonation. And the precursor for that deprotonation might look something like this. You might have a difluoromethyl group. We want to deprotonate this position to get to that type of a substructure instead of this internal position. Okay. However, when you attempt to do that deprotonation, either with strong bases or with weaker bases, you deprotonate the internal position. You deprotonate one of these two CH bonds there and not the terminal position. Why? Explain that to me. Hint, it's in the conformational control section. So we're talking about conformational control somehow. But that's the problem. Why don't we deprotonate at this position? Why do we deprotonate there? Okay, so you kind of have a few minutes to brainstorm that phys-org question. We'll be done with this one about 11:15. So I'll give you guys maybe 5 or 6 minutes, and then I'll talk through it with the other slides that I have prepared. Okay? Cool. Got it figured out yet?
Oh, yes, sir. Thank you, sir.
So then we could take up, even though it is not so acidic, but then we can take up from there. But then oh yes, but I think you were putting these bonds, or you could do put in the air.
Oh, depending on what type of conditions you use.
It should be higher.
It's a strong base. It's a weak base. Like you can do
Okay, weak base,
but high risk acid or high temperature and
and
high
low
temperature with a medium to strong base. Yeah, it doesn't matter what condition you use, that deprotonation is sufficient.
Okay. Yeah, it will.
That's why this
It's
will
all the stabilization. Do some scribbling. That's it.
Okay, we got this puzzle figured out? So let's think about deprotonation of a carbonyl to start. It's easy to draw on paper. It's more complex in reality. Okay, the C alpha position, it's acidic, right? We all had to look at the Evans pKa table, or we have it posted at our hood or at our desk, saved on our computer. Why is the C alpha position acidic in a normal carbonyl? Don't worry about the fluorinated things. Just let's focus about a normal carbonyl. So what makes it acidic? We can draw the arrows in, but we have a CO bond. So this would be the CO pi bond, right? And maybe the two substituents, one's coming at us, one's going back into the page. And we're deprotonating this proton over here, right? So there's a maybe we have HHH, methyl ketone. I'm going to draw so which one of those protons is acidic? Antiperiplanar. In order to deprotonate, the sigma bond, the CH sigma bond needs to align with the pi system. That's why it becomes acidic. As these electrons donate into the carbonyl, that leaves the proton hanging. This proton is easier to pick off because of those electrons are contributing into the molecular orbital with the carbonyl. So when we deprotonate, we require the CH bond to align with the pi system of the carbonyl. Okay, so that's why the alpha position becomes acidic. And now we can take this and apply this type of an understanding to the deprotonation of these difluorinated carbonyls. And specifically, this is what I just mentioned. You need the alignment of the CH bond with the carbonyl to acidify the proton and facilitate deprotonation. Now, when you have that type of alignment in this type of a difluoromethyl ketone, we need the CH to be aligned here with the pi system, but when that happens, the fluorine atom would be close in space to the carbonyl. The dipoles of the CF bond and the carbonyl would be aligning, and that's disfavored. Instead, because of electrostatic repulsion, these types of difluorinated carbonyls would typically exist in a different conformation, one in which the CH would be closer to the carbonyl. The CF bonds would rotate so they're away from the oxygen atom. And in this situation, this proton is no longer acidic. You don't deprotonate that position. We'll see if we can deprotonate something over here on that side. And so this is a different projection. This is your Newman projection here. Again, you can see this is the alignment that you would need to deprotonate, and that has the oxygen and the fluorine atoms close to each other, and there's electrostatic repulsion. Instead, it prefers to sit in an orientation that would look more like this, and with computational error, there might be a little bit of a difference from what I drew here, but it would tend to have the hydrogen closer to the fluorine atom. Okay, cool. Okay, so let's come down to, how do you do this? How do you make these fluorinated enolates? From a synthetic perspective, there are other strategies to make these that do not rely on deprotonation. So here's one example. You might take like a difluorobromo ketone precursor, throw in a reducing metal, like zinc metal, get to a zinc enolate, and then you can work with that magnesium metal. You can get to a magnesium enolate. Okay, so that's, oops, there's supposed to be one here. So that's one strategy. Just start with a bromo or an iodo or something else here. Another one might be a retroclason. So we can take a precursor like this and with an additive, deprotonate. If you deprotonate, electrons go down and we break the CC bond in a retroclason reaction. And that would also generate the enolate. Okay, so there are other strategies, other creative ways to get to these types of enolates that you can then use in chemistry, but you don't do it by deprotonation typically. Okay, cool. Is that a good way to end the morning session? And now we can go get our tea? Is it time? Okay, thanks. 10:15 on the dot. All right. We'll come back to another question in just a little bit, all right? Okay, we're going to get going again here. Is anybody else outside right there, or not right at the door? We can get going? Okay. So, yeah, we're back into tutorial mode right now. We did a problem over here, and I think discussion continued throughout some of the coffee time, and then as people are kind of migrating back. But are we good right now on that type of an explanation, a discussion? Okay. So let's go to the next one. I promised we would come back to this one, and the goal here in this next problem is to really walk through the details. Yeah, they're on. Maybe do I just need to bring them a little bit closer? Is that better? Is that better? Okay. Do you want me to I can just speak a little bit louder, if that would work too. Okay. So here we have this one over here. This is indinavir, and then the wrong epimer here with this hydroxyl group has flipped. We have on your slides, I think you have this exact one, right? If you flip forward in the slides, you get two more just blank slides. That's paper for you to work on. And so the goal here is to rationalize, you can see on top, rationalize the potency of the analogs. And so I've given you the substructure that we want to think about here. We want to think about the alignment of the alcohol with the fluorine atoms, and then think about how the R3 and R4 groups would line up. What's the favorable conformation for each of those substructures? So really quickly, I'll help walk you through it a little bit in terms of what we should do. We are going to have this compound A and B we're going to start with, okay? So we're going to think about the Newman projections and what would be favorable conformations if we're looking down this carbon-carbon bond and you want to draw a couple of Newman projections and try to rationalize which one would be the most favorable. Okay? We're going to do this 4 times. Okay? And so you have a couple here, and you have some extra space on another slide, or if you're using scrap paper to work on C and D also. Okay? This can take a few minutes to work on. Okay? We're going to come back, and I'll walk you through some of my thoughts on it in just a few minutes. Okay? You got it? Go for it. Yep. So for those of you who just came in, I'll talk off the mic. We're going back to that early example. When we think about Newman projections, that indinavir example. It's in the slide, I think you see it. But what would the favorable conformations look like from a Newman perspective for those things? And in your slides, you can see the other couple there too. So there's 4 compounds that we're ultimately going to discuss. Right now, I think we're just kind of working on A and B. So hopefully you drew a series of Newman projections, at least for the first one, and possibly move in the second one too. There's a couple that we might consider, and there's a third that we could also draw if we want to too. And what I'm doing here is just setting the primary alcohol as being one direction. If we're looking down, you go to the right, you would see the R3, and then if you're looking down from the alcohol to the left would be that hydroxyl group, and that's that stereocenter here. And then hopefully the stereochemistry on the backside is correct also. For this target, you typically need an arrangement of the R3 and R4, so they're kind of going away from each other there. And so when we rotate the CC bond such that we have a gauche interaction, remember the gauche interaction, kind of two features to that. You have the overlap of the CH bond with the pi star of the CF, and so that's reinforcing there. But you also have a little bit of an intramolecular hydrogen bond with the hydroxyl and the fluorine atom, and so that's another effect there. That holds you in a conformation. And this alpha fluorine here, in which it's syn with a hydroxyl group, that was the one in which the natural conformations seem to be consistent with the conformation of the one that does not have fluorine seem to match that of the conformation we put fluorine in this position. If we start rotating this around, you'll see some conformations for which you have the anti-arrangement here that's not necessarily favorable. You'll start to see these R groups are reasonably bulky, and we'll start to see steric interactions with those as you continue to rotate around. And so we have a situation here in which there's a preferred conformation. And so did most people kind of get something written down for B too? You're working on B. And so we can start looking at B. In B, when we have a gauche conformation, we start to have other steric interactions that are disfavored. Okay, so that's bad. In the situation in which we would have like R4 and R3 anti to each other, and that's preferred, we don't benefit from the gauche interactions there. We don't benefit from an intramolecular hydrogen bond either. And so these are the type of features that will hold the R3 and R4 groups into certain conformations. So did anybody take a stab at C and D? We got C and D? So C and D is the next couple that you should probably move into. I'm going to give you a little bit less time since we started doing the analysis and walked through A and B, so you should be able to work on C and D a little bit faster. I'll give you 5 minutes here, and then we'll walk through it with my slides. Okay? So I did make a mistake here. So what I'm going to do, I'm going to come back to C and D here. I'm trying to see if I copied everything wrong. So in C and D, you should have the opposite hydroxyl group there. And I think when I put it on these slides, I have the wrong hydroxyl group here on these slides. So apologies about that. So it seems like some people are slowing in their writing. And I put the correct C and D up here so we can go ahead and go over to the... Some other thoughts here in C. Again, it's the wrong C structure. The stereochemistry of the alcohol needs to be inverted. But in C here, since we have the wrong stereochemistry of the alcohol, we obliterate activity, but the fluorine makes it worse too. The fluorine amplifies the wrong conformation. And so, there's several thoughts in here. When you start drawing those conformations, you'll see several of them are just, a couple of them have competing effects. So the hydroxyl group has the wrong stereochemistry to start with. But then it also reinforces a conformation in which the R3 and the R4 groups, have this steric clash. So you're kind of pushing things away in one and then trying to pull them together in the other. So you don't have very good conformational control there. Of course, you can draw another structure for a trio there. For purpose of teaching, I'm just trying to focus on a couple of the conformations. So in the other case, we can use fluorine and that gauche effect to reinforce a conformation in which the two substituents are anti to each other again. So it's back to a linear conformation, and we regain some potency there. So it's not all the way back to a 2 nanomolar, but 20 nanomolar. And you can see how powerful this effect is at being able to control conformation in an aliphatic system and make sure that your large moieties are presented at the right vectors and engage the enzyme properly. So I think those numbers there are outrageously powerful. You have a 5 micromolar compound, and we get to a 20 nanomolar compound by the inversion of one fluorine with a hydrogen. That's cool, that's powerful, all right? So you can think critically about it. There are a couple of other conformers that you should be drawing as you're doing this assessment, but now you've actually walked through it a couple of times on your own, and you know how to deal with this problem in your own futures and whatever your drug design campaign might be in the future. Okay. So you can think critically about it and apply it in your own setting. So let's move on to another question here. This is a fun one, thinking about conformations of amide rotamers. So when we draw amides, many times we seem to draw one rotamer, but recognize amides have a couple of different rotamers, and you know that because when you take an NMR, many times you see the 2 rotamers in the NMR, and you have to heat it up, 100 degrees, 80 degrees, something like that, to get the 2 rotamers to coalesce into a single signal. In this case, the 2 rotamers are shown here that we're talking about. We have an amide rotamer in which the aryl ring is cis to the oxygen carbonyl, and another rotamer in which the aryl ring would be trans to the aryl ring. And the question is, which one of those is the active conformer? This is a real story. You can see the BMCL article down there. This team needed to understand which rotamer is responsible for the biological activity. So how would you use fluorine to probe the different conformations and establish which one is the active conformation? That's the question for you all. I'll give you a couple of minutes to think about that. Okay? You can talk through it with your friends if you want, and we'll come back and discuss their solution in just a couple minutes.
aryl group where nitrogen is there, amide nitrogen. That will preferably have left side of formation.
So you're saying if you fluorinate, oops, let me get my cursor over to the right screen. So if you fluorinate one of these positions over here, which one?
It will favor the left side one.
Okay. So that's one suggestion, fluorinate over in this area. Other thoughts or other questions or suggestions? Anybody else want to take a stab? Nobody else is bold and daring? Thank you for keeping the discussion going. Okay, so fluorination might be one strategy here, and so there might be several sites. So I'm going to give you about 30 seconds to make up your mind before we vote. And my gosh, I hope we get more votes than last time. No, get your answer. Go ahead. Yeah, get it ready. 6. Okay. So, A, B, C, D, E, F, G, H? Okay. I know. Okay, so we saw a lot of C's, D's, E's. There's a little bit on F there. So you can't see in the front. The people in the back know what everybody else voted. You guys might be cheating in the back, waiting to see whose hands go up and then follow. But okay, so here's the initial principle, and the principle we already discussed. It's trying to engage the NH in an intramolecular hydrogen bond, and also use the dipole alignments. And that's a disfavored alignment, so we want to rotate away from that alignment. And again, this would be a reinforced conformation. So this team chose to fluorinate both ortho positions. So very, very similar to what you're doing. My response was a bit of a trick response, which one? And they chose to do both, because if you do one, you can encourage the molecule to exist in this more of an extended conformation, and that if you fluorinate the other position, you can encourage the molecule to be more of in this bent type conformation. So they did both. Now, we did get a lot of C, so let's go back and think about C. There were quite a few votes for C. And alpha to an amide is definitely a strategy for controlling conformation, but it's not the question they're trying to ask here. That's looking at a different position. So when we're thinking about the amide, think about which bond we're rotating. We're rotating around this carbon-nitrogen bond. We're flipping the amide through this carbon-nitrogen bond to get between those two. While this is a good strategy for controlling conformation, their biological question was not about rotation of this carbon-carbon bond. When you fluorinate alpha, we're controlling conformation on this carbon-carbon bond over here. I'd like this example for that exact reason, that I get that response in my own students when they see this the first time, okay? So if we wanted to probe the conformation of what's going on over on this side of the molecule, totally, like you could use that strategy. But that wasn't the question that they were trying to ask in their current, where they were in the campaign at that point, okay? So it'd be a good solution, just a different question, different problem. Okay? Cool? We good? Do you want to see what their final molecule looked like in this series? Their final molecule you would expect to look something like that. Linear structure. One of these two is the pharmacophore. You're not sure which until you see the final molecule. And now there's been a lot of synthetic creativity, maybe design creativity to get from this compound over here to that one. You can see the hydantoin is still in place. You still have the 5-membered ring, benzanulated, that's still all there. But look at the substitution over here. We used to have an amide. Amides have an oxygen that's basic. Hydrogen bond acceptor, that amide carbonyl. And they've replaced that carbonyl with the pyridine. Lone pair of electrons on pyridine on the nitrogen are also basic, can engage in hydrogen bonding interactions. Now there's a little bit different vector between this carbonyl and that nitrogen, but you can still replicate the interaction with the target through this replacement. There's been a lot of changes structurally over here to this heterocycle relative to this guy over here, but if you think about the synthetic chemistry to get there, it'd probably be easier to make an alkyl halide and then just do SN2 chemistry over here and just SN2, 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 and keep replacing this moiety ultimately to getting, till they get a good inhibitor. Okay? Cool? Good discussion. Controlling amides. You have two different control elements on amides, as we saw before. We can think about controlling over here on this side. We can also think about controlling over here on that side. You have two opportunities to probe conformation. Okay. Questions? More discussion?
Sir, but there will be also electrostatic repulsions between the carbonyls, the two carbonyls.
Over here?
The two structures, there are electrostatic
Yeah.
repulsions, there will be there.
Sure, but you have, the way I have drawn it here, there's electrostatic repulsion, and you're right. So you have rotation around the CC bond. So don't believe that any of these chemdraw,
This would be,
yeah, the chemdraw structure is not static.
yeah.
And so you still have free rotation around this carbon-carbon bond, and that carbon, sorry, this carbon-carbon bond and that carbon-nitrogen bond. So it can move and minimize the electrostatic repulsion between the amide carbonyl and this imide carbonyl. Or urea type carbonyl, sorry. So, okay?
Also, like, sir, I have another question. Like here, then the pharmacophore part should be beyond that of the amide carbonyl, right? Because otherwise, this entire amide part and even the fluorine part, which is having so many interactions, that is getting replaced by the pyridine group in the optimized analog. Because if that kind of interactions are required for like binding with receptors and all, then that would be entirely hampered in this case.
What would be hampered if?
Like I'm asking that here the amide is getting replaced by pyridine group for rigidification in the optimized analog.
Right.
So like under practical considerations, that part should not have any binding with the enzyme substrate or the receptor part, with the receptor part basically.
You're saying this nitrogen should not?
Yes.
Fine. No, I think it does. I think it replicates the interaction that you used to have with that carbonyl. So you know, this is an early probe. It doesn't mean that this carbonyl is optimized for the right distance, right geometry. So you can still optimize that position. Okay, and if you can improve the hydrogen bond donating, hydrogen bond accepting ability, and maybe not the accepting ability, but just get a little bit better geometry there,
Okay. So then that is
you might get a more optimal hydrogen bond. Yep. Now, there are other things too in drug discovery. You're not only concerned about potency. So I don't know the full story here because they don't always publish the full story, but maybe there are other liabilities with this molecule, and by cyclizing, they could avoid some other issues. And then further regain potency by introducing this. That's hypothetical. They don't always publish all the details of all the studies, but you can at least see that they've tried to retain the hydrogen bond accepting capability at this position through a pyridynyl nitrogen for whatever reason.
Also the linear state which we maintained. In case of that, when it is for 55 nanomolar, the same geometry is in optimized analog, but when the rotamer, another rotamer, that is, if we replace in rotamer conformation the pyridine ring, that will be not that much potent, because that the rod shape like molecule should be needed for the better potency, I think.
So I didn't understand the entire thing. I didn't know the scientific description. So, yeah, go ahead.
That rod shape, this molecule is
This one's rod shaped. Yep.
then the optimized analog also rod shape.
Yep.
If we replace that the other one, the rotamer and
This one over here.
then if we replace with pyridine, that should not be the
It doesn't make like more of a pyridine over here.
Yeah.
Yeah. Yeah. So if we put a pyridine over there, we might not be able to fully control the conformation and control the projection of this other group at the right vector. Right? So I think that's what they've tried to do here, is really control the geometry for pushing it over here. If we instead this way cyclized over here, you'd have some conformational freedom, but it wouldn't force this moiety into the right position. Yep. Okay. So let's go back to 5-membered rings. Okay, 5-membered rings are fun. 5-membered rings are found all over biological molecules, endogenous biological molecules, and also drugs, therapeutics. And so this is a pair of molecules. These are nucleoside-based compounds. You can see the sugar. You can see the heterocycle. These are di-deoxynucleosides. Di-deoxy meaning you, in the normal DNA, RNA, ribose has both alcohols. DNA, deoxyribose, be lacking one of the two alcohols, would be lacking the alcohol at this position. These are di-deoxynucleosides, found in quite a few therapeutics. In this case, these 5-membered rings that bear a hydroxyl group and a nucleobase can exist in a couple of different conformations. And I've showed the different puckering that can occur. When you pucker one way versus the other, you can see the distance and the geometries. The relationship between the alcohol and the heterocycle shifts drastically. Now, for the enzymes that activate these drugs to function, you need to have the alcohol and the heterocycle in a certain conformation. So you need to try to reinforce the active conformation. Okay. So who knows what enzymes act on these? How do you activate nucleosides? How does RNA, as a monomer, what has to happen for it to get activated so that it can polymerize? Same thing with DNA. Phosphorylation. You have kinases, nucleoside kinases, that will put a phosphate on the primary alcohol. Then there's a couple more kinases that'll make the triphosphate. Remember ATP?
Yes.
Adenosine triphosphate, right? Okay, you need kinases to put on those phosphates at this position, okay? So in order for those phosphates to work, these molecules need to be held in the right conformation. So this question specifically asks you, just to take one of them, it doesn't matter what heterocycle it is. I drew 2 of them up there for you just to look at and think about. But take the alpha and the beta fluoro. If you have F up versus F down, which conformation will be stabilized? Okay? So what do you have to do here? What am I asking you to do? Which one's going to be more stable? If we have F up or down, that this position here would be there. If we have F up versus F down, in order to answer this, we're going to have to draw Newman projections. Okay. So think about putting F up and then draw the Newman projections. So up would be kind of over this way, right? Down would be down. Up would be over here, kind of an equatorial-like position. So put F up on both structures, put F down on both structures, and then start asking yourself which ones give you the appropriate gauche interactions. So there's what I'm asking. Put F up. Put F up, put F down. Think about how this might exist in either of these 2 conformations. And do the same thing with the bottom one. Okay, then we can start analyzing the problem and coming to a solution. So everybody is thinking about looking, like from this position, we're looking down a CC bond, right that way. So we're looking from this position to that position. Okay. Okay, do you want to start talking through it? Or do you want another minute? A couple minutes. So maybe some people drew some structures like that. We'll start with the one on the top. So if we put the fluorine atom, get my cursor over the right slide. Okay, so if we get the fluorine atom, it's going up here, and we look at the active conformation there, and the active conformation, we have gauche interaction and a gauche interaction, and then here's our CH. That CH would be the one that's not drawn right here at that position. That CH can overlap with the sigma star of the CF. That's the stabilizing alignment of the CH bond there. We have two gauche interactions. In contrast, when it flips over to this type of a situation, where would fluorine be? Fluorine would be over here, kind of to the right. Okay, so I'm trying to recapitulate that conformation over here. When we look down the CC bond, you have O left, heterocycle up, and then the CH would be down and right. When we're at this position over here, we would have the CC bond up and left, the CH, and then the fluorine atom would be kind of sticking out over this way. And when you have that conformation, you have, sure, we have a gauche interaction there, but you get no stabilization from an anti-periplanar alignment of the CO bond and the CF. So you don't get the CH donation of the sigma star that is a key driving force for gauche interactions. So this one would not necessarily be as stable because the CO is not properly aligned, or it's not beneficial the way a CH is in the anti-alignment. So here, this one would be stabilized in the active form. In contrast, when you consider the fluorine atom down here, This structure would be trying to recapitulate this. In this structure, again, you would have the CF, when it's down, would be presented over towards the right. The CH would be up. We look at the Newman projection, we would get something looking kind of like this. In this case, we'll have a gauche interaction there, but no stabilization from an antiperiplanar CH into the sigma star, the CF. You do not get a benefit there. And when we rotate to the other conformation, we have a gauche interaction there, but you do not see any of the CH contribution of the sigma star. So there's no real benefit in this one. It tends to be a little bit more flexible. So this one here would keep you in the active conformation a little bit more, and that would be the CF up. Okay. Does that an assessment make sense when we talk through it and draw them out, and hopefully people were drawing some things like that. Now, for your, and that's what we were trying to show here. In the active form, 2 gauche interactions, in active form 1, and same thing here. You also have the CH bond hyperconjugating there, and I try to put that in the text over here. Okay? So, we're not going to do this in class. I've given you another example that you can use to practice this same type of assessment. So you can walk through the logic with a slightly different example here. In this case, the fluorine atom is at a different position. You'd be thinking about these 2 structures here, and we would want to be thinking about the CF over here. In these structures, the heterocycle is a little bit too far away to participate, but we should still be thinking about the CH alignment of this proton here with the CF bond, and if we're going to be gauche with this oxygen atom in the ring. Okay, so if we rotate the position over, we need to do a slightly different assessment, but the basic principles are all still the same. So we're not going to take time in class to do this one, because I have 12:15. We probably need to do a different example that I'd like to move on to. And the next example is actually about the acidity of basic amines. This is a really fun problem. I like this one. We have 3 different amines. We have an N-methylpyridine that's protonated. And we have 2 derivatives in which the fluorine atom is either axial or equatorial. Okay, you see the difference there? Now, it turns out that those 3 compounds have different pKa's. So the question for everybody, which is the most acidic, which is the least acidic? Or rank them, 1, 2, 3. I guess if you have most and least, then the one in the middle is number 2, right? So I'm going to give you a couple of minutes to think about that and rationalize it. The most and the least acidic of that series. I want to do a vote of everybody in just a minute. Okay, got an answer real quick? Okay, so most acidic, A, B, C. Okay, so B's and C's are split. I didn't take a poll of every single person, but we'll say it's close to 50-50, just a first estimate. Least acidic. What's the most basic amine? A, B, C. Okay, so that one was A. There was a lot of B's too. Okay, went back and forth between A and B there, but there was very little C. So let me show you some data. These are not pKs. This is delta pKa. So N-methylpyridine, the pKa there of the conjugate acid at 9 or so, roughly. 8 basic amines, kind of 9 to 10 range there. Delta pKa, almost 2 pK units different, but what about that difference there? Axial versus equatorial matters when we're thinking about the pKa's. That's a crazy phenomenon. How do we explain that? And that's where the root of the question really is. It's the why. Okay, so do people kind of do this assessment yet? Have you thought about why the axial versus equatorial matters? Now that you have the data, take a couple minutes and see if you can rationalize it yourself. We'll come back and talk about it maybe 2 minutes, okay? Okay, so for the first part of the question, the least acidic, what was the rationalization there for most people? Least acidic, how would you rationalize this one here? A, or this guy? Least acidic, most basic nitrogen. Lewis basicity of the nitrogen.
Conjugate base would not have that fluorine with the hydrogen that doesn't have that kind of repulsive interaction. You will not find.
Well, repulsive. I think about the basicity of the amine. So if you have lone pair of electrons on nitrogen,
That base, that lone pair.
in order for it to act as a base, it needs to send its electrons to something. When you put fluorine at the beta position there, so alpha, beta, when you put fluorine at the beta position, the electronegative effect of fluorine starts pulling electron density towards itself, and it renders, through an inductive effect, this amine less basic. This amine will pull its electrons closer to itself because of the inductive effect of fluorine a couple atoms away, and that would be why these two are both more less basic, more acidic. Okay, it's a really important effect. We're going to come back to acid-base chemistry in the next lecture quite a bit when we start thinking about distribution of molecules throughout the body. It's going to be pretty important. But the directionality of that effect matters. It can be a conformational controlling element. It can also be a pKa modulating property. Now we need to compare these two. And this is a little bit trickier of a problem here. Let's think about the arrangement of the molecule, and when it's in the axial conformation, intramolecular hydrogen bonding interaction is present. We said that intramolecular hydrogen bonding interaction is stronger for the cationic amines. We had that series of like way too many structures on one slide. I don't like having that many structures on one slide, but there were a lot of structures showing the equilibria. And when you had a cationic species, that intramolecular hydrogen bonding was stronger. And that's one feature we're seeing here. You also have gauche interactions. So when you look down, this CC bond on this structure here, the fluorine and the nitrogen are gauche. For some people, it's kind of tricky to see the 3D representation when you have a 2D ring system. So you can make a model. You can go back to your lab this afternoon or tomorrow or in a week or never. It's up to you. And make this molecule and recognize that the nitrogen and fluorine are gauche and the CH bond that's in the axial position here is anti and has proper alignment with the CF sigma star. Okay? So that's what I'm trying to show here. You should be able to draw this structure from looking at that compound there. So that's favorable. And you only have it with this. In this case, where you have the CF bond, that CF is anti to the carbon nitrogen there. And you don't have the intramolecular hydrogen bonding interaction to further stabilize. So this is more stable overall. This is a more stable species. So this one is more willing to let its proton go. It's more acidic. Okay, cool. It's a fun example. It's a really hardcore phys org. Okay, it turns out that this can be useful. We're going to see this molecule on top again when we look at distribution. The modulation of pKa of basic amines is like one of the most important things in medchem. It gets used so much to solve so many problems. So we'll understand why in subsequent slide decks and subsequent days of the lecture. But just please note that this property and getting the directionality right can be useful in drug discovery. And this is a serotonergic agent from some years ago. This the Van Niel paper, 99, is this one here. So yeah, question.
So if the middle one is the more stable, then why it will exist into that third structure? The structure will exist like second one in there?
Yes, this is a thought process. If you have maybe other substituents that lock your ring system, you can get one versus the other. You can still measure these computationally and measure model systems that have this type of property. But think about if you had other substituents dangling off here, you could control axial equilibrium, axial equatorial equilibria by forcing it into the right conformation. In addition, you might have a rigid system. You might not have the opportunity to do ring flips and go back and forth between them because it's conformationally locked somewhere else. And the nature or the directionality in which you position the fluorine can have an impact. And it's also great phys org and great thinking, and that part is relevant too. Yeah. So.
These two are not conformational isomers. They are you cannot actually interchange, right? Conformational flipping will not interchange. So they are conformational isomers. So if you flip if you flip the middle structure, it will not go to the third structure. So that is what you are saying is not possible.
But you could deprotonate and reprotonate from the other side and then do a ring flip. Right? There's a way to get there if you, in a physiological system. You deprotonate, lone pair of a nitrogen tunnels, right? Tunnels back and forth through the nitrogen. Then a ring flip would get you, and reprotonation the other side would get you to the other structure.
So that's why I think you said that drug, the stereocenter doesn't matter over there.
Well, you would have diastereomers here, right? So you have a stereocenter here. When you have this fluorinated, now the two sides are differentiated, and then they're diastereomeric. So the problem would get a lot trickier if you move forward with it. So again, this is a thought experiment. This is a very simple model system that's meant to explain more complex systems as we move forward. Okay. Okay. So, I was told we should be done at 12:30. 12:29 and 37 seconds. We'll stop for the day. For me, thank you very much. There's more stuff going on this afternoon, so do come back later for the next lecture. Have a great lunch, and I'll be back up here tomorrow morning. Okay? See you all then.
No, I think we'll go on like 2 o'clock. I will go there, and then we will have a discussion between you and have a discussion.
Hi, how are you doing? My daughter made me take this on the trip, and she wants this to go everywhere with me. So on the first day, I don't remember who it was, on the very first day. Yeah, okay, yeah. So I had to take a picture. There you did, yeah. So I know it looks weird for a lecturer to come with a stuffed animal, but my daughter says I have to. So.
उसके बाद टॉपिक बाद डिस्कशन हाँ दैट विल कम मैं वहाँ
Sit down while we talk. Because I have to go to a lecture again for an hour and a half this afternoon. So, yeah. Right, right, and distribution The question is, why is this one still, this one kind of bonds, and this one doesn't? Why is this still So the question that I was asking, somebody else asked in my response, does this do from it's not going to do anything. Okay, so the question is going to come in this paper. Do they do an ANMR experiment with this compound? And what does the ANMR say about this compound?
So try to come back by
I
2:30, right?
don't remember. I didn't copy it into the spreadsheet. Do you want to read? It'll be one. If you want to read the whole paper right now, but you can find that part. It's due in one molecule. I don't think so. But that's speculation. I just want to say while we talk.
Okay, so truly speaking, you can understand that if you want to learn anything, the short 5 days course is not enough. But still, I think our overall idea is that we touch up many aspects of fluorine chemistry, so that many things can be done. As a course coordinator here, even my expertise was not completely in fluorine chemistry, so I involved like many other faculties, Dr. Ravi, who is today's speaker. He very kindly agreed to talk on some aspect because his expertise fall in that area. And we so far so we have looked into some chemistry aspect, how fluorination can be done. What Dr. Madhuri talked yesterday. So from there, today's idea is to that Dr. Ravi will talk to you about metal catalyzed fluorination reactions. So, and I'm very thankful to him for helping me out to complete this workshop well. So, Dr. Ravi has a very good experience. Dr. Ravi completed his bachelor's from University of Delhi, and then followed by master's again at the University of Delhi with organic chemistry as major. In 2012, he completed his master. Then he did his PhD from CDRI Lucknow, one of the premier institute for medicinal chemistry research. After completing his PhD in 2017, Dr. Ravi moved to Scripps Research Institute at California, USA, where he worked from 18 to 19, about more than a year. Then he moved to Harbin Institute of Technology, Shenzhen, China. This was just before COVID. This was in November 2019. So I can imagine what he has experienced over there. But then it was good that he could work there for 2 years, like sometime online, offline, and then followed by that, he's recently, before joining Naipur Mohali at our department of medicinal chemistry, he was at University of Bern, Switzerland, where he worked on photoredox catalysis, radical chemistry, sustainable chemistry, and synthetic method developments. Since January 2025, Dr. Ravi is at our own institute, and I feel really pleasure talking to him about his expertise in photoredox chemistry, radical chemistry, and we plan to work together on several aspects. His research interest lies in the development of improved and practical synthetic methodologies, synthesis of complex organic molecules which has medicinal applications, development of catalytic strategies which are mostly by light, electricity, and mechanical energy aspects, so that his lab want to develop sustainable approaches for this drug discovery as well as chemical synthesis. His areas also lies in the asymmetric synthesis, organometallic chemistry, organoboron chemistry, CH activation chemistry, and that is why I really asked him to give a talk about metal catalyzed fluorination reactions. So with this, I would like to invite Ravi to talk to you. Yeah, thank
you. Thank you, Dr. Deepak, for this kind introduction. And indeed, it's a very great pleasure of mine to present some of the work related to fluorination reaction using this metal catalyzed reactions. So first of all, very good afternoon to all of you. Hope you had your great meal. Your sugar is running in your blood. Yeah. So let's take the walk towards this fluorination reactions. So this slide, I guess you have seen yesterday. So since morning, since last day, we are talking a lot about this fluorination reaction. And this slide, I think Dr. Deepak has already shown yesterday, contains a molecules or a drug-like molecules which contains at least one fluorine atoms in the this drug-like candidates. For example, if you see some of the candidates contains more than one fluorine atom, which is called the trifluoromethyl group, but this molecule, how they are important, you can see the graph on the right hand side. There is an increased trend for this fluorinated molecule. If you see after this 2011, the fluorinated versus non-fluorinated molecule, the trend is rapidly increasing. so that it's making the 20% marketed drugs contains at least one fluorine atom. So as a chemist, as a medicinal chemist, I'm always interested in making these molecules. So we are fascinated with this fluorine, but how do you incorporate? So this is the question I always ask about as a chemist, how do you synthesize? So I propose this to my student as well. So how do you bring, achieve this fluorination reaction? So one of the strategy which is already existing is you start with the starting material having the fluorine. So now you make your drug-like molecules which already contains a fluorine. You do all your chemical manipulations. Just a second. Yeah. So you do all your chemical manipulation and you ended up with a drug which contains the fluorine atom, right? This is practically okay, but sometimes this fluorine atom, when subjected to different chemical reaction, you lose the fluorine, right? So there is another approach, which is the late stage fluorination reaction. So in that, you have a drug molecules, you'd synthesize from all those n number of steps. You have this drug molecule, and with the aid of some metal or some catalyst, you do the fluorination reaction. So by doing so, you directly convert this carbon-hydrogen bond to carbon-fluorine bond, which is sometimes is known as the CH fluorination reaction. This looks very good. You don't have to you don't have to rely on the fluorinated molecules. You incorporate the fluorine at the later on of the molecule and you end up with the molecule. But this limitation is always the reactivity, right? It's not possible always the drug molecule at the later on is reactive enough to undergo this fluorination reaction. And then there is another problem arises is the regioselectivity. If your drug molecule contains equivalent number of CH bonds, so selectively incorporation of fluorine is tedious and is difficult. So therefore, there are some methods people wanted to incorporate selectively. Though there is one method reported in 2009 from Buchwald group, where he converted these pseudo-halides, right, to direct fluorination reaction. So just converting these pseudo-halides with the palladium catalyzed reaction in a very extensive or a bulky phosphine ligands, you can get the fluorinated molecules. But again, this is very challenging. You have to synthesize all these ligands, you have to maintain the conditions, this harsh reaction condition, 80 to 130 degrees. So people wanted to incorporate the mild and the sustainable methods. So one of the strategy to incorporate the regioselectivity is the directing group strategy. Now what is directing group strategy? So you have a substrate, for example, which have a carbon-hydrogen bond you want to functionalize or you want to make the fluorination, and there is a directing group, which is a basic group which coordinates with the metal and make this kind of a species where you have a metal inserted into the carbon-hydrogen bond. Then now you can do a number of functionalization. For example, any fluorinating reagent which insert into this carbon-metal bond, and then you have this carbon fluorination at a regioselective position. So this strategy is very promising. People explored a lot in this direction, not only for the fluorination reaction, for introducing the different kind of functionalities. For example, if you look at this directing group coordinates with the metal, right? And then directing this metal to insert in this bond, making this kind of a cyclometallation species. And then after removal, ligand exchange and reductive elimination, you have this functionalization. So now look at what kind of functional group act as a directing group. You see on the right hand side, a nitrogen containing basic group. Any molecule, any atoms have the electron density, can coordinate with the metals, and then direct the metal to insert into the CH bond. So by doing so, this azaindoles, pyridines, pyrimidines, triazoles, this oxidizole, thank you, and this pyrazole, and this benzothiazole. They all contains at least one nitrogen group, right? They are all basic, they can coordinate with the metal center, and then therefore they are pretty good for the directing group strategy. Now, apart from the nitrogen, there are some weak coordinating group. Why weak coordinating? So they don't want to share their electrons, but still they share the electrons with the metals and then act as a weak directing group and undergoes the CH activation reaction. For example, this ketones. Ketones contain the oxygen center, which is a less basic, but still coordinate with the metal, and in some reactions you can have the CH activation with ketones. Similarly, you have this carboxylic group, ester, amides, and even these carbamates. They all connect as a directing group and then undergo some kind of a CH activation reactions. Apart from these groups, some other groups, for example, this hydrazine, nitriles, urea, in some of the cases, they have been utilized as a directing group functionality to do different kind of a reaction. But for our interest, our strategy is to incorporate fluorine, right? Why fluorine? Because we have seen fluorine is a very good molecule. But fluorine exists in two forms. You might have seen yesterday, fluorination. The fluorine, introducing the fluorine atom can be done by a fluoride ion, which is a good source, right? So commonly source is silver fluoride, is a very good fluoride source. And then the cesium fluoride and even the HF pyridine. They are very good fluoride source. But the problem with them, they do not undergo the oxidative addition with the metals. So people started to look out for some electrophilic fluorinating reagents. For example, one of the best reagents is select fluor. Now look at this structure of this select fluor. The fluorine is directly bound to the nitrogen atom, and the nitrogen atom contains the positive charge. So this bond is very weak, easy to break. Now the fluoride acts as a fluorine positive. Because the resultant negative charge is stabilized by the nitrogen atom, and therefore they are very good source for the fluoride ion. Similarly, there are another reagents which is NFSI. Again, the fluorine is a electrophilic source. The negative charge is stabilized by this 2-sulfonyl group and is a very good solid. So you can easily set up your reaction with this reagent. Then people later on develop another reagent which is NFPTI, this fluorinating pyridine, and they all work as a directing group strategy as a fluorinating reagent. So then what about the metals? What metals are very good for this kind of a reaction? So basically all these three atoms which are highlighted are very good for this CH activation reaction, and in particularly palladium and rhodium and ruthenium. They are best choice for the CH activation reaction. They are low valent transition metals. They undergo easy for the oxidative addition, and then they can easily have the multiple oxidative stage which is required in the CH activation reaction. So people explored this a lot in a CH activation reaction. So let's take first example for the fluorination reaction via this directing group strategy. So Sanford in 2006, he utilized this pyridine containing molecule for this fluorination reaction using this palladium catalyst. So by just doing the palladium catalyst and this pyridine as a fluorinating reagent, he could get the product with a microwave at 150 degrees Celsius with the monofluorinated product. So the yields range from 50 to 30, it's not bad, but for the starting point, it's a very good strategy to incorporate monofluoro group. And the mechanism, if you see, is for the orthofluorination. So the first step is the palladium coordinates with the nitrogen to form this palladium coordinated species, which undergo the CH activation followed by cyclopalladation intermediate. Now this intermediate, because this carbon palladium bond, so this bond is slightly nucleophilic, right? So the fluorine, which is electrophile, can insert into this bond. So again, palladium undergoes this oxidative addition, and after reductive elimination, the palladium is regenerated and get the monofluoro molecule. So this was the turning point. People started to explore the fluorination reaction using different directing group strategy. So as I said, people explored a lot of directing groups for different kind of functionalities. One of the directing group is this trifluamide. Now trifluamide is a very easy to prepare in a reaction, one-step reaction, and is a very good directing group. Now if you do the same reaction with the palladium and the same pyridine fluorinating reagent, so you ended up with a monofluoro compound. Now the best part with this monofluoro trifluamide, you can convert it into the n number of product. So for example, you cleave this trifluamide group to get this n-methyl compound. So from the single starting material, you get a different kind of a substrate. Additionally, you can oxidize this amine to the aldehyde. Now fluorobenzaldehyde is not easy to make, but with this strategy you can make the fluorobenzene, right? Similarly, yeah, please. ठीक है. Similarly, you can convert this triflamide to azide, which is another functional group required in a lot of biological molecules, right? You can convert this into the azide and everything. ठीक है. वो बाहर से ही होंगे. हाँ हुआ. ठीक है. So yeah, we were talking about the azide conversion. So you can convert this amide, this triflamide to azide. Similarly to cyanide, but simple conversion, right? And the best part of this cyanide, you can further oxidize and you can get this carboxylic acid fluorinated molecule. So the single conversion or single directing group strategy could lead to the diverse array of compounds. Now next comes with the phenol containing compounds. So we have seen this triflamide is a very good directing group, but phenol, which contains this pyridine, this again acts as a directing group for this CH fluorination reaction, right? That is fine. I think it's just hot. Yeah. So again this phenol containing molecule which has this pyridine as a directing group, suitable for this CH fluorination reaction, again with the palladium catalyst with this NFSI, which is again another fluorinating reagent. So this CH bond undergoes fluorination at the mono position, and if you have multiple fluorination or multiple sites for the fluorination, the selectivity guides. So now the regioselective CH fluorination of these molecules happen. So this strategy is pretty attractive because once you have this fluorination reaction, you can cleave this ether bond to get this phenol containing fluoride molecule. Again is a very attractive strategy to get this fluorinated phenol molecules. Another directing group which is very good is the oxymethers. Oxymethers again coming from the aldehydes, right? So you can get this oxymethers from one step from the aldehyde. This oxime then reacted with the palladium and again with the NFSI as a fluorinating reagent to get this fluorinated molecules. And the practicality they have shown, they have isolated this 1.4 gram of the product. So not only the milligram, you can get the kilogram or the gram scale of this reaction. So again, the strategy, you have this fluorinated molecule, you remove this oxime to get the aldehyde containing fluoride. Now this is not easy to get the monofluorination in a molecule. But with this, all these directing group strategies, you can achieve the fluorination. But then people later on explore the bidentate strategy. So instead of using one nitrogen group, so instead of having one nitrogen group as a basic donor, people started to explore the two nitrogen as a basic donor. Why? Because they can stabilize this palladium catalyst very much. So instead of one, the two can coordinate with the metal and can guide the CH activation reaction in a selective manner. For example, in this case, this amino acid derivative was subjected for this fluorination reaction using select fluor as a fluorinating reagent, and then they observe this regioselective or the enantioselective fluorination reaction. So if you look at the mechanism, again the coordination with the palladium of this two nitrogen takes place to make this intermediate. Then the base subtraction followed by CH activation form this carbon palladium bond. Now in this carbon palladium bond, this fluorinating reagent insertion takes place to get this kind of intermediate in a regioselective manner, and then the reductive elimination followed by deprotonation get the product. They observe the single diastereomer in this case. Why? Because if you look at this intermediate, the directing group is attacking only one side, not on the other side. So the fluorination insert in a enantiomer selective manner, and they observe the single diastereomer of this amino acid. They further confirm the diastereoselectivity with the X-ray crystallography, and they get the trans selectivity of this 2 functional group. Now again, the amino acid derivative was there, so people tried to explore to get the fluorinated amino acid. So in one case, if you remove this phthalimide with just hydrazine, you get this amino fluorinated molecule. Then if you remove this, this functional group to get the acid, it's again directly the amino protected amino acid, fluorinated amino acid molecule. So this strategy is also important to incorporate selectively fluorination molecule. Then later on, the simple amide, not the bidentate, just a single amide was also subjected, and they got this fluorination reaction. 20 example up to 77% yield, it's not bad. Then later on, people started to check the influence of the ligands. So because the ligand plays sometimes the important role in directing the CH activation reaction. Because if you see this step is always a reversible step. So the palladium always undergoes the addition followed by elimination pathway. So people try to stabilize this with some ligands. So in this case, this ligand 1 tries to stabilize this palladium catalyst, and then they get this 18 example up to 79% yield with the selectivity of the opposite selectivity in this same reaction. Then again, people wanted to explore the strategy without the directing group. So if you notice, the starting material already has some kind of a directing group which is directing the metal for the CH fluorination reaction. Later on, people wanted to make a directing group in situ, which is sometimes called the transient directing group in a reaction center, which does its jobs and after the reaction can be removed in a similar pot. So one of the transient directing group is this amino acid derivative, which reacts with this aldehyde, so in situ form this imine. Now if once the imine is formed, this is a simple stage for the CH activation reaction where imine nitrogen act as a directing group, and then CH activation takes place for this aliphatic carbon. So look at the mechanism. This directing group, this aldehyde reacts with the amine, this amino acid transient directing group to form this imine in situ. Now this imine undergoes this coordination followed by CH activation with the palladium, and then the fluorination takes place at this position, and then removal of this transient directing group and palladium gives the product without having the directing group in the molecule. So this strategy is very impressive. Without the directing group, you can convert the directing, by some simple manipulation, you can convert the functional group into a directing group and then can remove from the same pot. So again, looking at this strategy, people try to explore without the non-directing CSP3 CH fluorination reaction, where they just took this amine, the simple amine, which reacts with some kind of a this directing group, for example this aldehyde. Now this aldehyde have this amine followed by this hydroxy group, again a bidentate ligand, which coordinates with the metal and directs this CH bond to be activated and then perform the fluorination reaction. So again, simple amine, unprotected, nothing is a directing group, converted inside the pot, and then fluorination reaction takes place. So again, the mechanism, if you see, this transient directing group is reacting with the amine, forming the imine, and then you have this hydroxy group, nitrogen, which easy to coordinate with the metal center. So first coordination followed by this fluoride ion fluoride source insertion, and then removal gives the product. So this is easy to hydrolyze, so therefore it's not consuming in the reaction, and just 20 mole per sometimes 50 mole % is required, and then do its job. So this strategy is also important to convert a functional group which is not a directing group to make this directing group strategy inside the one pot strategy. So later on, people were already, established a lot of method with this CH activation strategy. While the emergence of this radical chemistry, people tried to explore how does this fluorination can be achieved with this radical intermediate. So people tried to explore this radical generation via different method and then capturing it with the fluorinated reagent to go the fluorine atom transfer reaction. So by doing so, you can incorporate fluorine atom in a aliphatic system and get the fluorinated molecule. So one of the strategy where to incorporate or where to generate the radical is the hat process, where you generate your radical from some other radical initiator process, which abstract the hydrogen and then generate the another alkyl radical. Now this alkyl radical undergoes different kind of a fluorination, fluorine atom transfer reaction and to form the fluorinated product. So one of the strategy was published in 2017 using the silver salt. So silver salt are usually good oxidant under the given condition. So when treated this benzyl containing this molecule with this, silver nitrate, this undergoes the oxidation reaction to form the benzylic radical. Now benzylic radical with a suitable fluorinating reagent, for example select fluor, undergoes this fluorine atom transfer reaction to form this monofluoro molecule. Now because of this one hydrogen already present in a benzylic position, this undergoes second oxidation reaction to form another stable benzyl radical, which again undergoes second fluorine atom transfer reaction to form the difluorinated species. So in a single conversion without a directing group, you can get the difluorinated molecule at the benzylic position. The problem with this radical process is the selectivity. So people wanted to explore how we can achieve the selectivity. So one of the strategy for the selectivity issues with the radical, if you make the more stable radical, for example the benzylic radical or tertiary radical, you can resolve this selectivity issues. So in all these cases, people always ended up with the benzylic radical species, which undergoes any one of the kind of a radical intermediate species undergoes the fluorination, so either the monofluoro or a difluoro species, and they ended up with a product. Then later on, people tried to explore the copper catalysis. So not only the silver, copper can also do the same job. And the important thing with the copper is you do not require in a stoichiometric amount as you require in a silver catalysis. So people explore with this copper catalysis who does the same job. So select fluor undergoes the single electron transfer to form this kind of a radical cation species, which undergoes the hydrogen atom transfer through the starting material to form this alkyl radical. Now this alkyl radical, as soon as it's generated, it undergoes the fluorine atom transfer reaction to form this fluorinated product, and the select fluor is consumed to oxidize the copper. Now later on, people wanted to explore without the oxidant in a reaction. So they did this radical CH fluorination with a photocatalyst. So photocatalysis is an emerging field which I am also involved to make the radical species. So people wanted to explore this photocatalyst to do this hat kind of a process. So one of the process which can generate the alkyl radical is with this tungsten based photocatalyst. So this the important thing of this tungsten based catalyst is when it's oxidized or when it excites with the light, it can easily undergoes the hydrogen atom transfer process to form this alkyl radical. So this alkyl radical then further capture with this NFSI or some other fluorinating reagent to form the fluorinated molecule. Now the issue arises with this kind of a catalysis is the selectivity. So once you have the multiple CH bonds which can be easily abstract with this tungsten based photocatalyst, so you can have different regioisomeric mixture form. For example, in this case, only single regioisomer is formed because the radical form is the tertiary radical, and this tertiary radical is stable, so therefore single product is formed. But look at these two cases. Both of this radical can form, which are secondary radicals, and then two mixtures of the product is possible. So therefore, this strategy looks promising, but it has some issues with the selectivities. Then later on, the strategy was revived, and to make the selective radical species was needed. So people started to make with the iridium-based photocatalyst, and then utilizing this N-hydroxythalamide as a radical precursor. So because in a photocatalytic cycle, when you excite your catalyst, it can undergo the single electron transfer to either oxidize or reduce the species. So in this case, this iridium catalyst is reducing the species to form this methyl radical. Now this methyl radical is highly energetic species. It can react with the fluoride to get this methyl fluoride species, or it can react with the starting material. For example, in this case, to get this another stable radical, which is a secondary or a tertiary. So this process, by doing this, is a hat process where it abstracts the hydrogen from the starting material to get this this methane gas and a stable tertiary radical. Now, as soon as this tertiary radical is formed, it has to complete the catalytic cycle where it gets oxidized to form this carbocation kind of a species. Now, this carbocation is trapped with this HF fluoride and then fluorinated molecule. So by doing so, you generate a radical in a selective position where it reacting particularly on the benzylic position. So for example, if you look at just a simple hydrogen atom transfer process, the hydrogen can be abstracted from this position or from this position. But by using this strategy, you generate the radical which is more stable, that is benzylic. So only benzylic fluorination takes place. So this strategy was also utilized for this heterocyclic molecules. So not only the aromatic, the heteroaromatics can also be accommodated, and you get the fluorinated molecules. So using the same strategy, the different group wanted to make the similar hydrogen atom transfer process, but instead of using this N-acetyloxybenzene, they utilized this TBPB, which is tertiary butyl phenyl perbenzoic acid. So now again, they reduce this guy to form this radical. Now this radical is a very good hydrogen atom transfer species to form this another radical. Now this radical again oxidize. The process is known as the radical polar crossover, where you either add or remove the electrons to the radical species. So this carbocation, as soon as it forms, is trapped by this HF with the pyridine and get the fluorinated molecule. The best part of this strategy is you can get the fluorination of the drug candidate at the later stage. So look at these molecules. The fluorination happens only particularly at this position. Nonetheless, some of the fluorination also happens at this position, and the racemic ratio was 5:1. But you can get the fluorination at the selective position, which is more stable. So in this case, again the fluorination happens at this position because this is a more stable radical species, and the fluorination happens at this particular position. And again with this drug candidate, the fluorination happen at the benzylic position because it's a more stable radical species, and with this drug candidates. So nonetheless, you can do a lot different kind of a fluorination reaction by applying the different strategies. So some of the strategies I just highlighted by using the radical or by the CH activation strategy. So when you wanted to make this fluorination reaction, it's always crucial what is required in a molecule. Okay, whether you want to incorporate the later stage or whether you want to incorporate the initial stage. Okay, so with that, thank you so much, and I'm happy to answer any questions. Yeah, yeah.
So can you go to the profile that we have
Where they first perform the pseudo halides, right? Yeah.
So here you have highlighted that in another expression where you have compared two types of reagents, cesium fluoride and other reagents.
Mm-hmm.
Where you said the cesium fluoride cannot undergo the oxidative
Addition, yeah.
So how these
So they did not mention about the mechanism. It's just a serendipity
Because oxidative addition is the first step during any catalysis.
in a catalysis reaction. Yeah.
So here also they have it.
So I assume the palladium is inserted into the OTF bond, right, and followed by some ligand exchange or something. It just forming this carbon fluoride bond. So therefore, it was the serendipity, and they marked the first conversion of the pseudo halides. But it's not later on. People never explored this direct fluorination reaction. So yeah,
Second one, sir, one more problem you highlighted over here, that temperature, right?
yeah.
Is required 80 to 130 degrees. But the majority of reactions that you showed, in case of Teslamide and all these things, there are also people are using 120 and 120 degrees Celsius temperature. So how you can see through this phenomena?
So these kind of a reaction for CH activation, as I say, if you look at this mechanism. So the first step is the substrate coordination followed by CH activation or cyclopalladation. This step is always crucial for this CH to achieving this CH activation reaction. And this step is reversible, right? So to make it in a forward direction, people make higher temperature of this reaction. But it's not necessary. You cannot do the reaction, this directing group strategy at the lower temperature. But in some cases, yes, you do require a higher temperature. For example, in this case.
And the third question, sir, in the radical chemistry, where you
Yeah.
showed the silver versus
Copper.
You compared copper, right?
Yeah.
So during explanation, you said like silver chloride, silver nitrate, right?
Yeah, it's silver nitrate.
Silver nitrate. So you said like is it for in stoichiometric amount?
In some cases, yeah.
Okay. But here
Yeah.
things are the in catalytic amount, right?
In catalytic amount, but most of the time, so for example, this radical formation with the benzylic. In this cases, yes, it's a catalytic, but most of the time it requires in a stoichiometric or sometimes super stoichiometric, because you are oxidizing this benzylic radical 2 times, right? So they require this in a stoichiometric or super stoichiometric amount. Yeah, that's the issue with this silver catalysis, right? But yeah, you can do some reaction, for example, this one with this catalytic amount. It's not, you cannot do this in a catalytic amount, but most of this time they require this in a stoichiometric amount. Yeah.
In that drug, that fluorination, there was there was energy excess. Fluid was stored in a stereo like that one.
This one.
So that way it's all maybe what you say given.
No, it's a diastereomeric ratio.
Yeah, but still like there is a it's 5:1.
It's a racemic ratio of fluorination this versus fluorination at this position. So because this is also a stable radical, the tertiary radical, which can undergo the radical addition, fluorine radical addition.
Is that the one at the benzylic position? It was selectively only.
Selectively, yes. Selectively forming in a 5 versus 1. Because the radical has to gain the stability. So benzylic radical is more stable than the tertiary. So
My question is that fluorine, that two forms, right, and dash form.
yeah.
So only one is formed?
No, they got both the diastereomers. I think they did not mention about the diastereo selectivity, but yes, in practically you get the 2 diastereomers. Yeah, the delta as a molecule we have synthesized in the first year, right? Yeah. Yeah, this one. Mm-hmm. F plus. F plus. So all this nitrogen containing fluoride, they supply this F plus, and the negative charge on the resultant nitrogen is stabilized over the pyridine ring. So they are good source of electrophilic fluorine over the nucleophilic fluorine. Yeah, this one.
NFSA.
Mm-hmm.
NFSA is applying F plus.
No, F plus, yeah. F plus. Because if it supplies the F plus, the negative charge is on nitrogen. Now, because of this 2 sulfonyl group, the negative charge is stabilized over to this sulfones, and therefore this negative charge is stabilized. So it's a good source for the fluorinate F plus. There are some reagents like, for example, this DEPSO or DBU fluorinating reagent, yeah, where you have this positive charge on nitrogen. Something like select fluor. Yeah.
So do you have any of these like catalyzed things in your planet in the lab for fluorination?
For fluorination, I'm planning one fluorination reaction. So not only to make the fluorinated, but to make the sulfonyl fluoride. Sulfonyl fluoride is a very good strategy for this click reaction. So recently, this Sharpless has introduced this SUFX chemistry, which is sulfonyl fluoride exchange click reaction. So you can do n number of chemistries with this sulfonyl fluoride molecule. So what I'm planning to make, the direct fluorination, direct trifluoromethylation, and sulfonyl fluoride formation.
I think I will say those all are the best molecules.
These are the good molecules, and especially I'm attracted towards this late stage strategy, right? So where you generate the radicals which abstract the hydrogen atom transfer, and then the resultant radicals, at the late stage you can do the fluorination. So I'm particularly interested towards this kind of a reaction synthesis or reaction development.
Okay, I think any more questions? If there are no more questions, we will thank Dr. Ravi. I kindly request Professor Bharatan to translate Dr. Ravi for this piece. So we will take a break now. Uh, so there is a tea and samosa is also there today, as a public demand was there. Yeah. And so we may take a little longer break because Professor Alban is at 9 asleep. So and Professor Bharatan is going to give his talk. So he also wanted to give that talk. So we will wait maybe 15 minutes from now. It's like 3:45. Should we start at 3:45? So if he comes, so otherwise he would join us. क्योंकि हमारे काफ़ी ड्राइवर्स काफ़ी उसमें बट just delicate driving. So we have other questions are there. So with other things that it means, other SPDs are. Welcome back in the last session for the second day. Today we have a very interesting perspective on organofluorine compounds. It is about pharmacoinformatics studies on fluorination chemistry. So for this we have a very appropriate expert who has a vast knowledge in this area. And you all know Professor Bhartam personally, but I still would like to, because I have few students, we are from Punjab University, so I really want students to know about Professor Bhartam and his immense contribution in the field of pharmacoinformatics as well as medicinal chemistry as well. So Professor Bhartam is a very good support for me, as whenever I think of NIPER, before even when I was at Punjab University, I never faced any problem, because I also did one GIAN course here in 2017, and whenever I approach sir for anything, he's always available. Not as I'm currently at NIPER, but even I was not at NIPER, and he's always ready to help for any academic activities. He's always available. So so really thank you, sir. So sir completed, got his PhD. Actually he did masters from Vishwa Bharati, Santiniketan, and then did his PhD in 1990 at University of Hyderabad. So his research experience lies in the organic synthesis and computer-aided drug discovery, which he is doing at NIPER over maybe around 24 years, 2001 onwards. Then molecular modeling of metal-based drugs. He did this work at Philips University, Marburg, Germany, for 1 year, 2002-2003. Theoretical organic chemistry. So he worked at Guru Nanak Dev University for about 7.5 years before moving to NIPER Mohali. He was a postdoc at University of Alabama, USA, from 1991 to 1993. Applied theoretical chemistry. He was a research fellow at the Hyderabad University, where he did his PhD. He has over 29 years of experience, including teaching experience of 23 years at Punjab University, at NIPER Mohali, and at GNDU Amritsar. So he had, while being a good teacher and a good researcher, he also took lot of administrative duties. He was the head of the department of medicinal chemistry. He was a head and in charge of Department of Pharmacoinformatics. I think he's the one who started this department itself. He was the associate dean academics. He was a dean at NIPER, our institute. He also was officiating director for a short span of 6 months. Then he got several awards and honors. He has a fellowship of Indian Academy of Sciences. He got OPPI Scientist Award in Medicinal Chemistry. He also got Ranbaxy Research Award in Pharmaceutical Sciences. Chemical Research Society of India Medal he got in 2008. He got Fellowship of the Royal Society of Chemistry London. He is a IBM faculty. He got IBM Faculty Award, and he is a recipient of the Fellowship of Alexander von Humboldt, on which he worked at Bonn, Germany. So he is a member of Research Council of CSIR CDRI Lucknow. He is a member of a Research Advisory Committee of ICER Mohali. He is a member Editorial Advisory Board of Current Computer Aided Drug Design. Member Editorial Advisory Board Indian Journal of Chemistry, and member of many funding agencies like DST, CSIR, DBT, and their research council. He has supervised 49 students. Then he has MS Pharm students 225, and I think this number is not updated, so it is he has guided more than maybe 225 students. A few master students also maybe at GNDU 16. Several research fellows worked in his lab, 12. Then several research visitors continuously visited. He got several grants. Number is big. Then he has total 385 publications to his credit, which has over 315 international research publications with an H index of 49. He has published almost all the good medicinal chemistry publication. I just wanted to list few, and because master students, I'm doing it only especially for first year master students, because I wanted you to have just such kind of dream to build this kind of CV. So you see, he has published in Bioorganic Medicinal Chemistry many articles, European Journal of Medicinal Chemistry, Bioorganic Chemistry, Drug Discovery Today. Then he has Chemical Review, Chemical, and so the number is more. I'm just listing the journal name. Then Journal of Organic Chemistry, ChemCom, Organic Letter, ACS MedChem Letters, MedChemCom, ChemMedChem, JMedChem, and then there is a JAX, an Angovanti Chemi, again many JAX. So I think really, sir, I think you are an inspiration to our department and to all the students and even to the faculty. So with this, I would like to request Professor Bharatam to deliver his talk. Yeah. Professor Arpan is here at right time. We just finished the introduction.
Well, Professor Salunke has got a lot of time to read my CV. Okay. Well, anyway, today my topic is on the pharmacoinformatics studies. I'm really happy that this conference, this workshop, we are discussing the entire science with reference to not only pure organic chemistry, synthetic perspective, but also with reference to physical organic chemistry, energies, conformations, and many other structural details. This is all part and parcel of our work in our lab. So that way we have learned many things to learn, and I hope my students are enjoying all that. Now I would like to start with this comment which I like the most, and I tell all my students so many times. This is title of this article published in JMedChem is "What Makes a Great Medicinal Chemist." So this Professor Murko, who is from Pfizer, he listed about 18 or 20 different characteristic features. Out of that, a few of them are most important. Out of those most important things is about thinking in 3D. That's what I also do that, and whatever achievements we had in our lab are mainly because we cultivated this habit of thinking in 3 dimensions about the chemical species. So I wish you to read this article, and this is worth reading for any medicinal chemist, whether he thinks in 3D or not. Okay, I took this idea because drugs are 3D objects, macromolecules are 3D objects. The interaction between drug and macromolecules happen in 3D. The dynamical processes are 3D. Chemical reactions are happening in 3D. To help in understanding all that, we have created a department called pharmacoinformatics, where we collected lots of software, and then we teach everybody how to think in 3 dimensions. The information technology we utilize extensively in this department for the drug discovery, drug development, drug toxicity, and other studies. We also use artificial intelligence technologies in this department. Having said that, I would like to add that point. When I started my PhD, none of these facilities were available. As a result, we needed to do everything in our mind. Now these facilities are available. You can use on your mobile also. 3D structural visualization and analysis is possible. So do adopt this habit. It will help you all. In pharmacoinformatics department, we do study all these varieties of concepts we adopt. QSAR is one which is extensively being used as a bridge between pharmacology and the chemistry. Then molecular docking, dynamics, virtual screening. In addition to all that, we also use quantum chemistry to understand various aspects, de novo design, chemoinformatics, bioinformatics, and all this, including artificial intelligence. 3D thinking in fluorine compounds. There are so many of these compounds are known already. We discussed many of them, but we are sure that if we know how our fluorine atom is embedded inside that architecture of the chemical compound in 3 dimensions, we do get much more clear idea. For example, look at these compounds. 2D structure as well as 3D structure has been provided. If the fluorine is at one end, we are okay. This is a green color is fluorine, but light blue are fluorine. We can probably easily top. Okay. Here, these are the 3 fluorine atoms in this molecule. But that's probably very straightforward. We don't have to think too much. But if we have it in little more complicated manner, we do need to think CF3 is okay. CF3 here also probably is okay in this molecule. If we go deep, we need more clarity. For example, in the next slide, I'm showing this is a 1D information about this compound. And then here this fluorine is, in 2D it is very clear, but look at the 3D, where is it? How it is embedded. When it is in 3D, we can rotate, we can zoom, we can represent in many ways. CPK models, for example, are also very useful. Likewise, there are new perspective is available when we think in 3 dimensions. So that's what I encourage all of you to adopt. Here, this is the light blue. No, this is green one, yeah. Right. So think in 3 dimensions will help you all. Anyway, let's go to the next slide here. So this topic of pharmacoinformatics we are applying in many fields. We started this as a topic of integrating bio and chemoinformatics, but we are applying daily for the drug discovery, drug delivery, drug metabolism, drug toxicity, and every field of pharmaceutical sciences we can apply information technology. Artificial intelligence can also be applied in every field, including drug delivery, drug toxicity, everything and anything under pharmaceutical background, maybe even pharmaceutical management, people also should be able to utilize this. So there are other names for the same topic. There are several synonyms. I don't want to elaborate on this. But I would like to tell that it is not difficult, especially for us, because our teachers in high school are pretty good. They teach very good mathematics. Compared to, sorry to say this, compared to American universities, American high schools, Indian schools teachers teach pretty good mathematics. Much more intense mathematics in high schools in India. So, so that is a good advantage for all of us. And so let us make use of this and get benefit. Informatics in pharmaceutical sciences can be 2 types. One is the science-oriented, the other is service-oriented. That means I want to say that pharmacy informatics, clinical informatics, healthcare informatics, there are so many varieties of databases, so much analysis is being done, and so much is practical. So how do we use all this? This is a flow chart to show how the data flow happens in drug. Once the drug is identified, before that, so many informatic technologies are practical. After the drug is identified, so much more is possible in this. So bioinformatics, some of you know about it. It's over 30, 35 years. It has become very popular, and mainly we use it for target identification and target validation. Whereas chemoinformatics we use for analyzing the data, chemical data in many ways. Virtual screening is one of the important possibilities, and for this purpose this symposium, we have Fluorobase is a database available of all fluorinated compounds. It is free of cost. You can download and use it at any time about these species. Then ADME informatics is also practical. Yesterday we discussed about this, and there are so many, we can optimize the ADME properties. I will give one example a little later. For toxicoinformatics, there are so many varieties of tools available like TopCat, Derek, Adult Expert. We can use any of them. For example, let us go to the day-to-day life where we are using fluorine. Every day, do you have sodium in your toothpaste? A big advertisement you have seen. I think when you were in class 5, 6, this was very popular in TVs. Now I am asking the question, do you have fluoride in your toothpaste? Inorganic fluoride. So there are so many compounds, sodium fluoride, SnF2, and all these species are generally available in our toothpaste. And these are all general inorganic variety. But how we are using actually? We are using to clean the bacteria. That means the bacteria which is settled early morning when we get up on our teeth, we want to remove them with the help of fluorine. Is it not biochemistry? Is it not enzyme technology? Are we not killing the bacteria? Yes, we are. So for us, it is a biochemistry topic. If a toothpaste is having fluoride ion. Similarly, let us look at the organic compounds. So many varieties of organic compounds. We listed many of them yesterday and today. Many of them are already approved drugs. Implications are many varieties. Some of them are anti-cancer compounds. Some of them are anti-fungal, antiviral, and antibacterial. Many varieties are already known. So this I don't want to elaborate. But now I want to go to a little more close. CF3. CF3 is present in many drug molecules, approved drug molecules. Again, anti-cancer, antibacterial. We can list many of them. Now, a few more are O-methoxy. Not only the CF3. For example, this was partly discussed earlier. Bioisoester for methyl. Many of the organic chemistry people are using. One more advantage with this is that if we have a methyl group and you replace with CF3, you will get a big IPR. Intellectual property is practically possible. For commercial perspective, this is also important. So many people are using this. Enhanced metabolic and chemical stability is practical with methoxy trifluoro compounds. Increased steric protection, high lipophilicity, improves permeability, reduced hydrogen bonding interactions, improved pharmacokinetics and bioavailability. These are all listed for the compounds with OCF3 group. First I showed fluorine, then I showed CF3, then I am showing OCF3 compounds. All these are available in these publications which we referred yesterday also. So, but then what is pharmacoinformatics doing with this? That I will come to this. Yesterday, Professor Altman has already described what is hyperconjugation and negative hyperconjugation. Let us consider this one more time because this is somewhat deeply involved topic. Hyperconjugation is a topic when a pair of sigma electrons are participating in delocalization. It is hyperconjugation because sigma electrons are donated. Negative hyperconjugation is when sigma bond is accepting electron density from the nearby. This is negative of the original hyperconjugation. That's why it is called negative hyperconjugation. This definition has been given by molecular orbital people. Other than that, this is already known in the glucose chemistry or sugar chemistry. It has an anomeric effect. Yesterday again this example came up. And so anomeric effect, which we learn in standard organic chemistry books, and the negative hyperconjugation we learn in advanced research articles. This slide, actually, this equation we have seen yesterday. You see what happened. Here the orbital overlap becomes very practical here. The lobes, the two lobes here overlap very much. What is here? It is a sigma star orbital. Between the carbon and the fluorine, it is an antibonding orbital. When electron density from this center is pumped into this particular antibonding orbital, the carbon-fluorine bond becomes weak, and then fluoride ion gets out. This was what I was explained yesterday. The same thing, I am using the same equation here. But we have to be somewhat careful. If a fluoride ion is floating in the body, it is probably not very comfortable situation. So, for example, this compound is approved for topical use. Probably because of the fluoride ion in vivo may not be very safe. Now let us go to this question. What are first order interactions in chemistry? Sigma bond is first order. Pi bond is also first order. Then there are second order interactions. Just we already discussed hyperconjugation and negative 2 hyperconjugation are second order interactions. How do we understand them? How do we evaluate them? There are push-pull influence. Under some conditions, fluoride ion pulls the electron density. Some conditions, fluoride ion can pump electron density into the given system. How do we analyze all that? Can we get the result quantitatively? For that, there is quantum chemistry. Quantum chemistry helped in the form of NBO analysis. It provides a shortcut to analyze this. We can estimate the energy due to a particular second order interaction very easily. We can analyze the first order also, but that is much easier to do. Second order is a little more tough to analyze. For that, this NBO analysis helps. What we need to do is that we need to obtain the wave function. To obtain the wave function of a given drug molecule or any organic molecule, we need to solve the Schrodinger wave equation. When we solve the Schrodinger equation using either molecular orbital theory or the density functional theory or any other advanced theories like coupled clusters or configuration interaction or many body perturbation, when we use all that kind of quantum chemistry, we will come across with something most standard that is called wave function. We identify a very well defined wave function for a given compound. That wave function carries lots of information. Almost every information that we want to extract is a part of the wave function. That is postulate 1 of quantum chemistry. Using that, we need to supply that wave function from quantum Gaussian calculation or any other software to this particular NBO software, which will analyze the various interactions. And the second order interactions can be estimated like this. Energy due to a given specific second order interaction can be estimated like this. It is due to charge, that is the total orbital occupancy into the Fock matrix, square of the Fock matrix element, and energy difference between the electron donating orbital versus the electron accepting orbital. This is a very simplified equation which is helpful in interpreting the wave function to understand what is the extent of the second order delocalization that is happening. How much negative hyperconjugation is there? What is the energy associated with it? Is it 0.2 kilocalories or 25 kilocalories? There is how much importance we need to give to in a particular environment for the second order interaction. To analyze all of that, there are these facilities available, and students in our institute, they are utilizing this information almost every day. The role of fluorine in pharmacokinetics. For example, here, look at this example. the modulation of pharmacokinetics is possible by introducing extra substituents which carry fluorine. That was partly discussed with a couple of examples earlier. I am showing another example here, which was part of our, for example, here there are several pharmacophoric features. Here, anti-cancer based pharmacophore, for which one feature here is hydrogen bonding feature. Another feature here is due to the fluorine center. Hydrophobic moiety is here. So there are so many of these which can be further modulated with the help of additional fluoro group introduction. This is helping in enhancing the metabolic stability as well as the membrane permeation. This was published recently in 2021. Now let us take this example which we have pursued recently. There is a target called FTSZ. This is an antibacterial target. It is a protein. The protein gets polymerized. The polymerization of the protein, if we can stop, then the bacterial growth can be stopped. Because once the protein gets polymerized, that means the FTSZ protein, if it is polymerized, it forms a linear chain, and from that it forms filaments, and these filaments actually are bound to the cell wall and they cause cell division. If the cell division is happening fast, then the bacterial cells grow at a faster rate. If I want to stop that, I can inhibit FTSZ polymerization process. For example, Staphylococcus aureus FTSZ polymerization. For that purpose, this particular compound has been identified as a prodrug. It is a difluoro species here. Now, this compound is known as a prodrug, and it can be bioactivated to give you this particular drug. This compound is known as PC190723, a very active inhibitor of the polymerization. However, they found that it cannot be made into a drug. When it cannot be made into a drug, what modifications are required? It is mainly because of the metabolic instability originating in this particular benzoyl or pyridothiosyl fused species. Then, due to this corner, metabolic stability is very much less. As a result, can we modify this? The idea was that can we introduce CF3 group in place of the CL. That is very much practical. Lots of examples were already available. As a result, it found that this compound, this chloro species, may be getting converted into the OH group. Due to this reaction, dechlorination followed by monooxygenation. The same thing does not happen when you have a CF3 group here. So TXA709 is a better prodrug because it does not undergo this reaction. That means metabolic instability is removed, but metabolic stability is introduced, and this active drug is TXA707, which is obtained by simple hydrolysis. Look at this. This is a species which can easily undergo hydrolysis, and it will give you the ortho and para difluorobenjamide. This is a pharmacophoric feature. This pharmacophoric feature is required for the drug action. What is the drug action? It is the prevention of the FTSZ polymerization. So this kind of simple modification helped in realizing a new prodrug and the new drug. It is still in clinical trials. It has not been approved yet. And so what to do with this? We can do molecular docking, understand the 3D structure of the FTSZ protein and how it is showing the drug action. This is a protein. There are two sites of action. One is the GTP binding domain. GTP binding domain is suggested, has been suggested as an important site of drug action. Another site of drug action is the IDC domain. It is known as, what is IDC? Come on, who is working on IDC? Interdomain cleft. Okay, I don't remember all the time. So interdomain cleft. It was suggested that this compound may be binding to either GTP domain or the IDC domain. So in that context, if we do molecular docking, this is a powerful pharmacoinformatics technology. What we did, we docked this compound and all other related lead compounds inside the GTP binding domain as well as in the IDC domain. It has become clear to us that when the compound binds to GTP binding domain, inhibition is not sufficiently high. Inhibition is pretty good, and in future lead compounds we should design by exploring the binding pose of TXA707 inside the IDC domain of FTSZ. That is exactly being done in our lab, and based on that, our students have found a few compounds which they will not tell me that is secret. I will not tell you right now, but they have found compounds which are nanomolar active compounds for antibacterial effect. That secret will come out after patent publication soon. But only thing is that their fluorine is not there in our lead compounds. We will explore that in the near future. Okay, now let us look at other examples where naturally occurring organofluorides. In nature, are there any organic compounds? Are the plants producing fluorine containing natural organic molecules? When we want to understand that, generally the perception is that nature does not incorporate fluorine in many organic molecules. But there are a few specific examples like this which are available, and then fluoroacetate is a major component. This fluoroacetate happens to be a dangerous compound. It's not a very favorable compound for consumption. So humans, they know which plant sources are poisonous and which are not. But animals, they don't know. They do consume all sorts of leaves. So if at all animals consume these kind of plant sources which contain these chemicals, they finally produce this particular metabolite, and this metabolite is leading to their death. So some plant sources are causing death to the animals because of this most dangerous. Inside the plant metabolism, this is okay, this is safe, because this particular species produces acetic acid inside the plant. There is sufficient mechanism is available to get rid of the CF bond inside the plant, but in animals it is not available. As a result, this species is poisonous to animals but not to the plants. So plants are happily surviving. So look at which compounds are there. Here fluorocitrine. This active reagent can interact with citric acid and form this kind of a complex. This fluorooleic acid is one, and fluoroacetaldehyde. Of course, these two are very much related to each other. And then this kind of metabolites are also found, and many adducts like this were also noticed, and several, not too many, a few specific. These were all reported in this particular article. So how does it work? For all that, there is an enzyme available. This enzyme is known as fluorinase enzyme. This fluorinase enzyme, what it is doing is, it is taking this kind of natural products, and then it is cleaving the CS bond and introducing the CF bond. This is the purpose of this particular enzyme. How it is getting the fluoride ion? It is probably getting from the inorganic sources. Fluoride ion is coming from the inorganic source to this particular enzyme, and this enzyme is transferring to the organic substrates. So this kind of chemistry is happening, and finally this not so safe metabolite is being generated, and so we need to be aware of this chemistry whenever we do drug discovery with natural product compounds. And there are some talking studies were done how this fluorine is binding to the enzyme, how it is actually transferring the fluoride ion, and several studies have been carried out. I am not going to elaborate on that. Now the entire chemistry associated with this symbiosis has been described very well. I hope some of us will get benefit, and these are all the ways in which the animals are getting affected. Similarly, some of the chemistry has been described, especially the citric acid cycle is affected when this kind of fluorocitrate is generated under biochemical conditions. So if there is no fluorine, citric acid cycle is normal, it is happening. If there is a fluorinated agent is present, the citric acid cycle is not taking place, and that is causing the dangerous side effects. So now I will go to the next set of examples based on artificial intelligence. Artificial intelligence is a very important topic. All of you know it is becoming very popular nowadays, and almost every drug discovery scientist has to learn this. This is realized by Naipar Mohali, and we are teaching this for the last many years. Especially now this has become compulsory course for every Naipar student in the coming few years. So what are all the various topics? Machine learning techniques, deep learning techniques, generative artificial intelligence. Likewise, varieties of artificial intelligence technologies have become available. How drug discovery people are using. Now, before going into that, I will explain there are several internal mechanisms. One can write programs, one can write tools, web-based tools are available. We can use many of them free of cost. Some of them can be obtained and we can utilize them, and we can develop our own tools. This is practical and many varieties of things. For example, knowledge-based systems. This is one type of artificial intelligence tools. For example, Google is a knowledge-based system. We are using every day. And the grammar checks in our word processing is all knowledge-based systems. So that we are using. Fuzzy logic, it is based on the fuzziness associated with the logic. It is coming from the physics called chaos. Physics or chaos. There is lots of physics associated with that. From that, a few things are learned and are applied to the mathematical logic, and tools have been developed. And then genetic algorithms, from the process of genetics that are happening in our day-to-day, from one generation to another generation, lots of principles were identified, and those principles were applied to artificial intelligence, and several tools were developed. There are genetic algorithms. Then explainable artificial intelligence is one of the latest technologies, because earlier versions of artificial intelligence was called a black box. It does not explain how it arrived at a result. Now latest in the last 3-4 years is to consider only that kind of artificial intelligence which will explain how it has come to a particular result. So this is also being adopted by the drug discovery people. Knowledge-based systems, for example, there should be an inference engine, there should be a knowledge base, there should be a fact base, rule base, and lots of things are there. For the last 30-40 years, this has been in the vogue. Genetic algorithms, we are using them in molecular docking. for example, to find out which pose is to be considered as the best pose and which pose may be neglected when a molecule is getting docked into the macromolecule. To decide, we do use genetic algorithms. So several software which we are using daily, Gold and Glide kind of software, are adopting the genetic algorithm based technologies in the background. So this is coming from artificial intelligence. Next technology is based on the explainable artificial intelligence. I told that there are tools like XAI, referring to the explainable artificial intelligence is coming into picture. This is very latest. 4 or 5 years ago it was introduced, and then it has got several internal mechanisms like transparency, justification, informativeness, and uncertainty estimation. All those things are coming from statistics but applied to heuristic knowledge. Thus, it is becoming explainable. Let us take into account how we can use, how we are using in hypermodeling. Let us take a few examples. For antibacterial activity, we are employing them. This fluorinated derivatives and flavonoids and chalcones, all of them are supplied as an input. When we generate an artificial intelligence model, we need lots of inputs. The more data we supply to train the model, the better it is in performing in giving the good results. So we supplied lots of information like this, and their associated antibacterial activity information. When we do that, we can develop several tools for antibacterial research. These many publications have been already reported in the literature. Taking clues, we have adopted for antifungal. Some people have used artificial intelligence, using generative artificial intelligence, and for antiviral also, several groups people used fluorinated compounds. Now, what did we do? Okay, before going there, I have to do what did we do using quantum chemistry. Several of the metabolites are electrophilic in nature. If a metabolite is highly electrophilic, it can be dangerous, it can be toxic. The electrophilicity index can be calculated. A standard organic molecule which has got a omega value that is called electrophilicity index about 3 is reasonably okay. If the electrophilicity index is less than 3, the metabolite is safe for human. If a drug is producing a metabolite with electrophilicity index less than 3, that compound is safe. If the electrophilicity of the metabolite is more than 3, we should not use that kind of drug in our drug discovery process. It's a simple, we can use rule of thumb. So what do we need to do? We have to consider the electrophilicity of the drug as well as all possible its metabolites. So for that, one of the major ways of measuring the electrophilicity of a metabolite is to calculate the fluoride ion affinity. If a metabolite is there and if its ability to interact with fluoride ion is of the order of 60 kilocalories per mole, that means the electrophilicity is very small. It's not dangerous. If the fluoride ion affinity is more than 100 or more than 120 kilocalories, it is dangerous. So to measure the electrophilicity, we do this kind of work. We take for example, we take a triazole-based nitrinium ion and we bring a fluoride ion close to it. When a complex is formed, how much energy is released? This is the 2D structure and this is the 3D structure. Here you can see there is strong pyramidalization at this nitrogen center. We calculate the energy released. It is less than 90 kilocalories per mole. That it is less than 100 kilocalories per mole. That means the triazolium ion is not dangerous. But if this triazolium ion is fused inside a cage like environment or peri-fused environment, again it is increasing, the electrophilicity is increasing. And then if it is fused in this way, electrophilicity is maintained. So we need to know under what condition which metabolite is giving what type of electrophilic metabolite. For that we are using this in everyday research, and these are some of our publications in this year on this topic. Now there is this multimodal deep learning model was developed by a set of scientists, Zhang et al. This is a publication in 2025 given here. So what they did, they developed a deep learning artificial intelligence model called AFCPI. The title of this is fluoro substitution compound protein interaction model. So this is what they called it as AFCPI. Using that, they could understand the activity cliff phenomenon in a set of compounds. Using that, activity cliff refers to a situation in which two structurally similar molecules exhibit significantly different activity values. This is how they used this kind of a concept and developed a model with the help of more than 100 million compounds, 100,000 compounds, and they trained the model across 2,500 protein targets with the help of these kind of the measurable quantities associated with biochemistry. And this model was used in an artificial intelligence network called encoder-decoder. Encoder and decoder. Encoder is to learn from the input and decoder is to provide the output. How does it happen? This is the chemical structure, one-dimensional information of a chemical compound containing fluorine. You can see the very first element is fluorine. And then this is the 2D structure. This is called the fingerprint of the same molecule. That kind of conversion is made before doing the artificial intelligence. And then data is supplied to the model, that is encoder-decoder model. And then when you decode the data coming out of this trained model, you can generate a few new molecules. This was the algorithm that was adopted, and they found that these kind of molecules can be generated. For example, if you have a compound with CH3, if you replace it with CH2F species, then there is a possibility of increasing performance in terms of the IC50 value micromolar level to nanomolar level. One can convert. This was a suggestion coming from artificial intelligence, and this compound was synthesized, and it was indeed realized that this artificial intelligence model has helped in really designing a set of improved drug-like molecules. Similarly, in this case, CH isopropyl group has been replaced with CME twice F unit, and then marginal improvement was noticed in this case, and likewise a few examples were given, and they were all discussed in this article. So this is what we did. We took several compounds from Campbell, like 55,308 compounds we have considered. They are all having antibacterial activity from the database. We have pre-screened them for IC50 value, for their drug action details and others, and we choose about these many compounds for initial training. Then after training, we got a model called antibacterial LSTM model, and then we have this was a generic model for antibacterial drug discovery. But now we have to fine-tune them. Fine-tune for a specific protein target, that is FTSZ protein. For fine-tuning, we have chosen 572 compounds which were specifically referred as FTSZ inhibitors. From this, we came up with a new model, and this was divided into two varieties. One is the GTP binding type, the other is the IDC binding type. Once we did that, new molecules were generated using CADD. These new molecules were validated with the help of traditional computer-aided drug discovery approaches. For example, pre-processing was done, tokenization was done, then the smile notation was created. This kind of one hot matrix kind of matrices were generated from the input, and such data was applied to the LSTM based deep learning approach. Then once we do that, this is the architecture of the LSTM model. This is how the data flow happens in this, and this kind of data flow actually helps in processing. There are several varieties of neurons here. There are several layers are available. Some layers are known as forget layers, and some are processing layers. Some of them are carry the memory from one cycle to the another cycle. So there is lots of detail. There are several details associated with this kind of architecture. Once we did that, we designed these compounds. Our generative artificial intelligence model was employed to design new compounds. It has suggested this kind of fluoroderivatives as as a result. These compounds were suggested for the GTP binding domain, and these compounds were suggested for the IDC domain. In IDC domain compounds also, we have fluoroderivatives, and for example, the amide group is replaced with this acetyl group. Likewise, a few compounds were designed by the artificial intelligence model. Then we had to validate them with the help of molecular docking, then pharmacophore mapping, then comparing with the physicochemical properties, Lipinski rule and all others with the known lead compound, and finally we could see which are the important interactions which are helping in the improved activity of this class of compounds. Next step for us is to synthesize this and then test them indeed. In another work, this is about anti-cancer drug discovery. The pharmacophoric features can be identified with the help of artificial intelligence, which is hydrophobic pocket, which is the hinge region binding center of the molecule, which is a hydrophobic center too, and which is solvent accessible region. Likewise, we can understand, for example, the green portion is the hydrophobic pocket number 1. All the molecules enter into that. Look at this, fluorophenyl group is entering into the hydrophobic pocket of the EGFR enzyme, and that kind of information helps in a big way in designing new compounds. These results were not our work. This is published work from literature. Similarly, using that, they have designed, they have understood the pharmacokinetics, halogen versus dipolar interactions. They have understood hydrophobicity, electronic tuning, and varieties of physicochemical modifications have been carried out, and the results were published in this journal. Another of our work is associated with anti-cancer drug discovery. Here again we have used LSTM type of modeling. Here this is still not ready for discussion. I'm just showing that this is one result we got, and again we got these kind of compounds suggested by our artificial intelligence model. It says that consider the aromatic ring systems containing these 3 fluorines in this corner of this amine derivatives with CF3 you consider. This is the suggestion coming from the artificial intelligence work that we have carried out. So now I will go to the next details of this fluoro base that is already available. I think I am running out of time, but I will quickly finish. This is a database developed by Mulka and other scientists. This database currently contains over 20 distinct groups of reagents, including methoxylating and fluoroalkylating compounds, with the largest groups comprising more than 50 entries. Likewise, this is the opening page of this database, and this is some of the details. Fluorinated agents database. Data were collected from diverse sources, including literature, reports, crystallographic databases, chemical repositories, PubChem, and other things. And then structure-based search is possible in this database. Smiles notations can be utilized to search, and then additional functionalities for filtering the search is also possible. 3D structures are available, and homolytic and heterolytic bond dissociation energies have been included in this database, and such databases are very much useful for any scientist who wants to carry out research. This database also incorporates the F19 related spectral information. For example, once we search, we can quickly come to these kind of results. Depending on our search query, we will come up with this kind of result. Whether that compound of our interest is present in our list or not, we can easily do. This is a chemoinformatics based. We can use Wiener index, or we can use Tanimoto coefficient. Likewise, there are so many chemoinformatics tools we can utilize in this database. Similarly, fluorobase can be has been utilized to identify some important chemical species. This is application reported in the website itself. So I would like to conclude here that pharmacoinformatics, whether it is based on chemoinformatics tools or molecular docking tools or artificial intelligence or simple quantum chemistry is not simple. It is very complicated, no doubt. But we are using a simplified version of quantum chemistry in drug discovery, like NBO analysis and the fluorine ion affinity, fluoride ion affinity, that kind of things. Using all that, we can get lots of information. The very first thing, the beginning of the entire thing, is to think in 3 dimensions. I am sure those who do it will certainly succeed. Small as well as macromolecules, 3D objects. Rational design is possible. Incorporation of the fluorine-containing substituents has demonstrated remarkable influence on both pharmacokinetics and pharmacodynamic profiles. Strong electron withdrawing nature, high lipophilicity, and metabolic stability and other related properties are being exploited in the medicinal chemistry. Most of these properties can be analyzed with the help of pharmacoinformatics. Of course, we have to give experimental validation towards the end of the project, but lots of homework can be done with the help of pharmacoinformatics before going into organic lab. These effects collectively contribute to greater chemical stability, reduced oxidative metabolism, and improved ligand receptor complementarity. That is what is the strength behind pharmacoinformatics in fluorine chemistry. These are some of the publications from our lab. This is the team which is working. I should agree that we are not focusing our work on fluorine chemistry, but we have several examples which contain fluorine as a substituent in our compounds. This entire presentation was compiled by all of them, mostly led by Ms. Rupal, and everybody contributed 2 or 3 slides in preparing this. So I thank all of them for this nice presentation. Thank you. Yes.
Thank you, sir, for very nice collaborative journey in the different parts. I was wondering, like the fluorine, like we are enjoying that lecture. So you were saying that it also goes into the binding pockets, the hydrophobic, the fluorine interacts with the hydrophobic domain of the protein. So how does that happen? Because this fluorine, that is actually, it has strong electronegativity, right?
Right.
It has a little bit of polarity in this kind of case. And in the hydrophobic pocket, when they go, what do you mean? Like you need to have a violet aromatic surface, which should be like a little bit
like leucine, isoleucine, and phenylalanine, that kind of amino acids, which form a sub-pocket inside the main pocket. And it is found that in our all our examples, that the CF3 containing units are majorly entering into that kind of sub-pocket inside the main pocket of the target, like EGFR example, FTSZ example, and as well as in the artificial intelligence based docking when we did. Everywhere we have found that.
Also like specific to aromatic side chain based amino acids, where like
Even if we have fluorophenyl group or difluoroamide group is present, this amide group is interacting in a hydrogen bonding fashion. But the 2 fluorines are not really forming any hydrogen bonding interaction. It's not exactly hydrophobic in the case of difluorophenyl difluoroamide group, but it is that fluorine, we searched for that, it's not forming any hydrogen bonding interaction with any of the NH centers. So that's what surprised for us also. But generally, we found that some of the discussion, even OCF3 group is also going into a hydrophobic pocket. So this was the observation.
In one of the papers which I was reading, like in my presentation, and which I showed, what I read, that fluorine, because of the very high electronegativity, it induces that CH bond never into like in the pocket, there is CH bond, that CH bond gets polarized, and so CH becomes now the hydrogen donor.
okay.
So mostly that.
So that is like a London dispersion kind of things, the induced dipole.
Kind of. So that majority of the hydrogen bond by the fluorine compounds was with CH donor. And other than, but yeah, definitely there was NH and OH were also donors, but majority of the hydrogen bond with CH. So because that fluorine was inducing adjacent CH to fluorine negative. I would say that.
On several interactions on Friday morning. Like, I was curious about the details of that too, but I kind of fell from the structures. But maybe we could relook at those crystal structures or docking models after.
Yes. Yeah, yes, certainly whenever we don't have all the crystal structures available, but certainly wherever it is available, it is very informative.
Yeah, even we are curious to understand the receptor in different molecules, the usually database you want to work. Anything else?
Any other questions?
Maybe that lies the thing like on the previous curiosity driven question is that I've seen that many of these fluorinated compounds they are pretty much biocompatible, and right, and then they have also shown that they have a very nice pharmacokinetic and pharmaco.
Yeah, that is a big advantage. In fact,
Big advantage.
as the molecule is floating in all body fluids and reaching the site of action, that is all pharmacokinetics. And if that is facilitated by our substitutions, it will be nice. A few examples we have seen today morning also we have seen a few examples. And I am sure in the coming 3 days we are going to have many more examples of the same.
I think with this I request for Salman to join so that we can celebrate Professor Barton. Dr. Ashish, you also to join for a photo. Okay, so this ends today's talks. And so tomorrow morning again we have a long day already planned. So tomorrow morning tomorrow is Wednesday. So and there is no class, right? So do you want to start is it okay? 10 a.m. we should start or 9:30? Can we start? So Salman?
Whatever, yeah. I thought you were asking everybody.
Generally they have a 9 to 10 class and tomorrow they have off. So is it okay that we start at 9:30? Okay, and then maybe afternoon lecture also 12 to 1:30. So we can start maybe instead of 2:30 we can start at 2. So that will be done by 4. Right? So that is the small change and I will write in the group.